Ladies and gentlemen, welcome. Welcome to the PIC International. Welcome to the pilot lines. Welcome to the high sensors. Welcome to the AngelTech Online Summit. My name is Jose Pozo and I'm here with Francesca Moglia, chairing the pilot line session, the session in which we want the companies to work together. And it fits very well because this is what I do for a living, getting companies, getting 557 members of EPIC working together. What I would like to share with you today is how a group of friends have managed to interact with the European Commission and enable Europe as the key place for the manufacturing of photonic devices. We have worked already on this for almost a decade. But in the last 6 years, we already have started 6 pilot lines on manufacturing of photonic devices. We have JEPIC's pilot line that manufactures indium phosphide photonic integrated circuits, MIRFAB on the mid-infrared spectrometers, PICS for Life on the silicon nitride-based photonic integrated circuits focusing mostly on biosensors and healthcare, PICSAP packaging photonic devices, Fabulous, the one that is making a difference for the micro-optics manufacturing in Europe. And listen to me, micro-optics manufacturing in Europe is going to be huge. And MedFab, medical devices for the industry, all the way to clinical trials. These are technologies that Europe have been excelling already for 3 decades. These are technologies that have developed strongly thanks to the support of the Photonics 21, the public-private partnership signed with the European Commission. All these European projects that we all have applied and succeeded have become technologies mature enough to go to the market. These 6 logos are the ones that are taking those technologies to the market, to the street. And we are working with them to make sure that every company in Europe benefits for that. On one hand, we have the companies who can supply, and these are not closed clubs. We are looking for new suppliers. And on the other, we have the companies who want to innovate, who want to make a new product into the market. This is not a research. This is to make sure that you have all the supply chain needed to go to the medium and even high volume production. I would like to share with you what I have learned myself on this. So basically, the Photonics European pilot lines have been already seen in Europe and in the world as seeing that Europe is leading in certain technologies, in silicon photonics, in indium phosphide, micro-optics, biosensors. They have positioned Europe as the leading place for manufacturing for industry, manufacturing a high readiness level. At the same time, we also have managed to engage with the large-scale manufacturing centers. Right now, we are not only focusing on niche markets, but later on, maybe from the presentation from PICSAP, you will really understand the boom that we are making already in markets such as consumer electronics or high-speed data interconnects. And in addition, we also have managed to address a wide range of end users in every market in the world. We have traveled worldwide to medical exhibitions, to environmental monitoring exhibitions, and talked to the top companies to address the fact that in their next products, photonics has to be a key enabling technology. And at the same time, in the next products, the manufacturing of photonics can be incorporated by the European supply chain. And in these days of the COVID-19, many people are looking for a job in photonics. I work in photonics. I love working in photonics. We have created the website, the biggest website in photonics to find a job in photonics, www.jobsinphotonics.com. So you are either looking for a job or you want to fill the job openings in your company, do not doubt, www.jobsinphotonics.com. That's all I had to say apart from one thing. This event is about cooperation. So if you have any question, please post it in the Q&A and we'll read during the Q&A. It's gonna be very interactive meeting because it is a AngelTech EPIC meeting. So we want everyone to interact. And with this, I have the pleasure to introduce our first speaker today, who coming from the European Commission has been the driver on bringing the companies and the institutions together to do photonic innovation. John McGann, it is my honor, it is my pleasure to give you the stage and hear from you the success story that the European pilot lines are. Thank you very much for being with us this afternoon. The floor and the attention of everyone is yours. We have John still muted. We have to unmute you.
Sorry, no, but I uploaded the presentation.
Yes. Francesca will play the presentation for us. I would like to first give you the good afternoon, of course.
Thank you.
It's been quite an amazing couple of weeks with everybody working from home. Francesca, when you want, you can play the presentation. Don't be surprised that you're going to get a lot more proposals for the next calls because everybody's at home writing proposals. You will see how amazing it is.
It's been crazy because the last few weeks have been all sorts of actions on COVID. I can talk about that maybe at the end of the presentation.
Where you may be in the world.
Fantastic.
I'm John McGann, and I'm Deputy Head of Photonics Unit at the European Commission. It's an honour for me to open the session here today and present you with a brief overview of the PIC pilot lines, which we feel are, with some justification, are a true European success story. I'd like to start with taking a quick overview of the European photonic sectors. Europe is a strong player overall, and particularly in a few key areas such as production technology and particularly industrial lasers, machine vision, medical technology, lighting, defense and security, optical components, and communications. Okay, we're a bit less strong in displays and IT. But what's important to note here is that not only are these sectors growing compared to other sectors or compared to the world GDP growth, but they're also growing compared to other European sectors. So in other words, European photonics is strong and overall getting stronger. Now, unfortunately, these figures are all pre-COVID, and we're not quite sure how things are going to work out over the next few years, but we can be pretty sure, I think, that the relative importance of these sectors is still going to stay the same, perhaps with an increase in medical technology and communications, so that we can tackle future pandemics or continue to function in a locked down world, or when we need more remote connectivity, more remote sensing and actuation. Now, to take a look at the photonics projects that we are funding inside the European Commission through the Horizon 2020 research program, as you can expect, there's a wide range of photonic sectors and technologies that all have particular requirements when it comes to manufacturing. And this led us to consider what we could do to support photonic manufacturing in Europe. And we decided what would really help would be pilot lines, as to support the many small European photonic companies to bring their good ideas into products. I borrowed this slide from the PICSAP presentation, so you'll probably see it later on. We had a review of the project earlier this month, but I chose it because it shows the essence of what we're talking about, supporting the transition from lab to fab, taking new technology prototypes from small volumes and scaling them up through a technology transfer into high value manufacturing together with training of the people. So what are the objectives of the European pilot lines, photonic pilot lines? Well, we want to enable high-tech SMEs in Europe to scale up their good ideas and validate them with customers for commercial production. We want to give the SMEs easy access to the services and infrastructures that they needed, together with providing the necessary expertise. We want to ensure this is done in as cost-effective way as possible so that the barrier for the SMEs to pilot manufacturing is as low as possible. We want to do it through engagement with the potential customers as early as possible in the product development process. And finally, and very importantly, the pilot lines should become sustainable, economically sustainable after the 4-year project cycle, so that they will no longer need public funds to operate, but can be financially independent, while still maintaining the objective of having a low barrier for the SMEs for manufacturing. So that's so much for the theory. Now let's look at the pilot lines in reality. We have 7 of them to date. Now, almost all of these are PIC pilot lines. We have PICs for Life, which is using silicon nitride technology for PICs operating in the visible range for applications in health and food. MIRFAB, which is mid-infrared sensing PICs for applications in the chemical industry and many other applications as well. PiScale, which became Litius, that addresses OLEDs on flexible substrates. Impulse, indium phosphide PICs, which is based on the JPICs platform, and they're presenting also later on. Fabulous, which is recently launched, and that deals with micro-optics for many applications. MedFab, also very recently launched. It's not on PICs per se, but it's really a whole range of photonics technologies for medical device applications. And finally, last but certainly not least, is PICs app, which is a pilot line for photonic packaging technologies. Now, we're very proud of all of these. And I think most of them are presenting later in this session today, so I won't do them the injustice of trying to describe them or their achievements in any more detail, because I think they're quite well able to do that far better for themselves. So what are the lessons learned so far? Well, first of all, we've learned that it's very important to engage with the potential customers as early as possible in their design process, because this creates a win-win. It's easier for the customer, it's also easier for the pilot line providers. Secondly, it's very important to build trust and to create lasting partnerships, because that means that subsequent cycles of product design and manufacturing is easier. Thirdly, by standardizing designs and interfaces, and by creating design rules, this also makes it easier to reuse technologies and reuse techniques and to shorten the design time. Fourth, it's very important to strike the right balance between openness and confidentiality. And I think some of the presentations later today will address this topic. Fifth, it's not just about providing a pilot manufacturing service, but also complementing this with other services such as training of staff and even staff placement, so that they can really learn on the job and then reuse this in future design cycles. And finally, right from the beginning, it is important to work towards economic sustainability and independence, so that when the public funding has run out, the pilot line is able to operate autonomously. Now I'd like to present some of the calls for proposals that are still open and that are PIC related, just in case any of you still have time and energy to prepare research proposals. These calls should already have been closed by now, but the deadline has been extended due to the COVID crisis. So first of all, there's this call for research and innovation actions in a range of technologies for a total research budget of 47.5 million euros. And the PIC topic here is calling for advanced technologies in the packaging, assembly, module integration, and testing of PIC components and modules. These should have an impact in reducing the production costs by a full order of magnitude, so thereby accelerating the introduction of PICs onto the market. The second call topic is for research and innovation actions like farm to fork, sensing, and new PIC technology building blocks. And these have a total assigned budget of 30 million euros. The PIC technology building blocks here should form part of comprehensive PIC integration platforms for both established and new applications, meeting the demands of the technology roadmap on sensitivity, efficiency, speed, and integration density. And the results should improve and include a validation with PIC prototypes at the fabricators. And finally, looking ahead to the future, we are now preparing for the new research program, which is called Horizon Europe. This will run from 2021 to 2027. The first work program of this research program is currently prepared, and that will describe a list of research topics that will be called for from 2021 to 2022. We're hoping that it can be adopted and published by next March, although with the current COVID crisis, it's not at all clear, because there's a lot of discussion as to how the research budget and even the overall European budget should be allocated. But we're quite confident that photonic technologies will still be a very important part of this, together with other key digital technologies that addresses the cluster in digital industry and space. One very important characteristic of this new program is that the topics are going to be structured around the expected impact, which means we'll probably be less prescriptive as to the details of the technologies and more describe the impact that we would like the technologies to have. So that's the end of my presentation. I'd like to thank you for your attention and leave you with some useful links. And now, if there's any questions, whether through the forum here, or feel free to address them through using these links, and we can follow up bilaterally in the future. So again, thank you very much.
Thank you very much, John, for a great presentation, and thank you for keeping us all up to date with what is happening. If there are questions, of course, I would like to repeat what John just said. You can just put it in the chat or in the Q&A. I have my first question, because keeping us up to date, the biggest thing that's happening these days, of course, the horrible, horrible situation the world is living with the COVID-19. From the European Commission, is there any action taken for that?
Yes, I'm very happy. Just hot off the presses today, we just launched the second call for expression of interest for COVID. There was a first smaller call in January, and this second call has been launched today, and that's with 122 million euros of funding. And one part of this, a big chunk of this, is very relevant for Connect technologies, including photonics. And that's got 56 million euros worth of funding for innovation actions. And this is looking at technologies that are very close to the market, that are very, very mature, I should say. So we're not talking about basic research here at all. We're talking about technologies that are almost ready to go onto the market, that can get CE certification. And but unfortunately, given the urgency of this, we've got a very short deadline. The deadline is 11th of June. So people will need to get their acts together if they want to apply for this. If there's two types of projects really that we're calling for, the smaller ones will be without third-party funding, and these could be, say, for projects of 2 to 5 million euros each. Innovation actions, and then the larger ones, if there's something like a digital photonics hub or some kind of body that can take on board third-party funding, that they can apply for the funding and then do what we call cascade funding. So even if the high-tech SMEs aren't ready to apply for this call directly, they can apply for a call organized by one of the projects subsequently. So that gives a little bit more breathing space of a couple of months to do that. So thank you, Jose. You're presenting the link there. There's a webinar on this taking place tomorrow morning at 10 o'clock. That's organized by the Photonics 21 platform. So if anyone is free to participate in that, we'll go through these slides in much more detail and the topics in more detail. And maybe you'll also get a chance to meet some potential partners there.
So this is quite a big prize for the attendees of the meeting today, because the call was announced today. And also for me, it makes me very excited because it's focusing on very high TRLs, looking for TRL7, very fast time to market, a very fast reaction from the European Commission on this very societal problem. So on this, I would like to congratulate you and all your colleagues. That's quite outstanding. Definitely. Are there any questions from here, from the chat, or from also the universe of people following us? I think we have a lot of questions, a lot of discussion. There's going to be a little bit of a panel later. Let's put the pilot lines into perspective before we go to a deeper discussion. I just want to have some question that I have for you, which is the future. So would you talk a bit about the kind of things that you could share with us about the vision? But we are about to change into a new program. If you could tell us how the pilot line concept is going to evolve, I would appreciate.
Okay, well, we're not quite there yet. I mean, the new program at the moment, we really only have very, very broad strokes. So What I can say at this stage is that it's going to be much more focused on impact, as I mentioned in the presentation, so that we're going to be maybe less prescriptive on the technologies, and that a lot of these key industrial technologies will be kind of grouped together. So we expect a lot more integration, that there won't be maybe separate areas for each of the technologies, but that because it's going to be objective and impact driven, that there'll be a lot of scope for, say, cross-cutting between photonics and, say, microelectronics and so on. But photonics we expect to have in lots of different places, because the draft text I've seen so far we'll have photonics for industrial applications, as well as sensing, and lots of scope for PIC technologies. But unfortunately, I'm not at liberty to go into any more detail than that.
We want to know, we want to keep knowing that photonics is key.
Yes.
And for as long as you guys do that, we are super happy. Thank you very much for a great presentation. We're going to have a lot more discussion in the later part of the meeting, but we continue with the program. And I would like to introduce the second speaker, which is also a very close friend of mine, Robert Harrison. Robert Harrison is sort of the person who is helping every company that wants in Europe with their IP protection. And I would like to also say a few words about him. So basically, he's an experienced business executive with almost 30 years experience in advising clients at the interface of technology management, business development, and intellectual property. His focus is on developing intellectual property portfolios and commercialization strategies for startups and small and medium enterprises, particularly in the field of semiconductor, electronics, biophysics, and guess what? Photonics. He has advised investors on legal aspect of intellectual property and its value, as well as on third-party infringement risks. But what's more important, I've been going around the world and I've been trying to sell pilot lines everywhere. And the first question I always get is, what happens with my IP? And that's why for me it's super important to have Robert telling us what happened with the IP and the manufacturing pilot lines. Robert, thank you very much for being with us. The floor and your presentation is going to be for everybody's eyes as of this moment.
Thank you. Thank you very much indeed for the opportunity to talk today about intellectual property and its role in pilot lines. We subtitled this talk, Getting the Legals Right. But in fact, in these 10 minutes, it's going to be extremely difficult to actually try and get everything right. So what I'm trying to do is to give you a little bit of a flavor of some of the issues that have cropped up when contracting with pilot lines in order to produce devices, packaging, new methods of manufacture, or the like. But firstly, a little bit about myself. I've got a physics degree and a PhD in 3-5 semiconductors. We were trying to grow indium gallium arsenide phosphide lasers using liquid phase epitaxy many years ago. Subsequently, I worked for IBM, where I did a diploma in intellectual property law, and I'm now a qualified European patent and trademark attorney, as well as being registered in France and Germany. And currently, I'm working on advising a large number of small and medium-sized companies, mostly in the field of semiconductor physics, photonics, and similar subjects. But first of all, I'd just like to review what we actually mean by intellectual property. Obviously, some of us think we know quite a lot about it. We've done diplomas in intellectual property, but the legal requirements of intellectual property are somewhat different than what most scientists and engineers would think about. The legal terms we often use are patents and copyrights. But if you start thinking about it, data rights, use of access to data is also part of that valuable know-how that you possess. Even trade secrets, manufacturing secrets, know-how, and what is sometimes called show-how, how your engineers and scientists are working in the labs on the production lines. That is actually valuable intellectual property that your company holds. And sometimes it's not adequately considered by legal laws. We know, for example, that the European Patent Office has its issues with some of the patents that have been granted in software. We know that the European Commission is thinking about how can we actually legally protect data? Can it be protected as a property right, or is it something special? Those are issues that are going to come up in the next few years increasingly as we move into the new generation of manufacturing. But first of all, let's come back to the pilot line case. And just to try and show a typical case, a very simple case, this is basically how a pilot line works. I don't think I even need to tell you about it. A customer is interested in having a device manufactured, some packaging being done. It doesn't have the facilities to do it, or its facilities are just not adapted to what it wants to try and achieve. But there's a number of pilot lines out there, sponsored maybe by the European Commission, maybe by national governments, maybe being set up as commercial opportunities by independent companies who are actually prepared to manufacture those products for the customer. And the customer receives the devices. Hopefully they're what the customer expects. And maybe the customer decides that it needs to scale up and it needs to actually move across to a commercial manufacturer, could possibly be in-house. It's quite clear, I think, in most cases, that what the customer expects for the scale up will actually get the intellectual property from the pilot line that is actually able to scale up. And generally, there will be contracts in place to do that. A more interesting scenario, however, comes when new intellectual property is developed. Let us suppose that what the customer brings to the project and what the pilot line owners, their scientists, their engineers bring to the project actually forms much more, actually creates new intellectual property. What are we going to do about that? It's not an uncommon scenario. We know that this happens very often. But does it mean that the customer owns the intellectual property that's been newly created? Or does it mean the pilot line owner and operator has access to that intellectual property? Can the pilot line operator offer it to new customers? Can it use it for its own research and development? Can the customer transfer this new intellectual property across to the commercial line if it wants to scale up the manufacturing process? With no agreement in place, it's not clear. The way the laws work in different countries around Europe are different. In some countries, any newly created intellectual property has to be jointly owned. Both parties agree about agree about the use of that intellectual property. Both parties have to be agreed that one of the other parties can use it exclusively. In other countries, it's different. In other countries, both parties can use the intellectual property themselves without even consulting with the other party. And sometimes at the most, there may be the obligation to transfer some funds across to the other party as compensation for the use of their intellectual property. What we need to be thinking about in those cases is really how we're going to manage this intellectual property that's been developed. We need to have an agreement on the use and the development of the new intellectual property. Maybe we even need to have an agreement on who pays for it. Normally, it's quite normal that the customer would pay the pilot line for actually producing the devices. But if more comes out of it, who actually pays for the new development? And one of the other questions that pops up from time to time is the question of, can I even file patent applications? Should I even file patent applications on this newly developed intellectual property or not? Maybe if I file those patent applications, I'm actually going to reveal trade secrets held by the pilot line operator. I'm going to be telling the pilot line operators, customers, competitors about how the manufacturing goes on. And maybe the pilot line operator doesn't want to do that. That really all needs to be set out in a contractual agreement, including questions about the general right of use or non-use of the new intellectual property. Maybe compensation for the use of the new intellectual property. in the future by the pilot line operator or by the customer. It's possible also to restrict it to the field of use. I'm only going to use this for laser devices at a certain bandwidth, or I'm only going to use it for laser devices made with a certain material system. Other solutions including time limiting, project limiting. This is I only want exclusive use for 3 years, or I'm only going to want it for a particular project. Those are certainly solutions that pop up from time to time. But things can get unexpected. We're recently involved in a case with a major electronics manufacturer. It wasn't so much about pilot lines from the photonics field, it was all about how to recycle some of their electronic products. An agreement was agreed with a small German innovative recycling company. And it was great. It actually involved new developments by the German company in order to recycle a particular electronic product. And everybody thought that this was fine until the large electronic manufacturing company came along and said, these are our general terms and conditions. And hidden among those general terms and conditions was a provision which basically said, if you use my intellectual property, the electronics company intellectual property, and you develop new products, new intellectual property yourself, I, the electronic supplier, am the sole and exclusive owner of this newly developed intellectual property. This was going to be a major problem for the recycling company because it didn't want to work exclusively with this electronics manufacturing company. It knew that it would be using the funds to develop new intellectual property. It had already programmed that into the costings. It hadn't actually appreciated that the electronics company was expecting to get exclusive access to that. And given the fact that the recycling of electronic products is a major field, it wasn't entirely it didn't agree with that at all. It could have removed a large amount of the business from the recycling company. And not only that, it would have actually meant that the electronics company, owning all of the intellectual property, could easily move to another company and engage them with the recycling process, leaving the original company high and dry. And if that sounds strange, the same electronic company was recently looking at some photonic suppliers with a similar sort of terms and conditions. So those are some of the issues that we've popped out. It's very difficult to actually explain within 10 minutes all of the issues involved. I'm happy to answer any questions. Thank you very much indeed, and hope you have a great day here at this virtual conference. Thank you.
Thank you very much, Robert. Thank you for a great presentation. Thank you for positioning the huge challenge, which is to keep IP on the customer side, while at the same time keep increasing the knowledge base of the pilot lines. I think there are so many questions that we could think and discuss, but I have one that is the one that I'm getting the most myself, which is many of our customers, they are worried about where to protect the technology. I know that you have to study case by case, but is there any rule of thumb here? Should we worry about China, or should we do it worldwide? Should we protect first Europe? Is there any kind of process that you would recommend?
Yeah, so I mean, thanks very much indeed, Jose, for that introduction, and indeed your question. And firstly, anybody who spotted the mistake in that video is eligible to get a small prize from me. And I apologize for it. The second point is that we're talking about intellectual property and how to protect it. A lot of the intellectual property in the pilot lines is actually done in manufacturing knowledge, what the show-how, as some people like to call it, what the engineers, the scientists have it in their head. And it's probably, and in many cases, not even worthwhile filing a patent or anything like that on that, because you have to share the information with the rest of the world. And manufacturing knowledge, if you share it with the rest of the world, everybody learns what you're doing, and you may lose some of your commercial benefit. That, of course, is different from some of these EU-sponsored commercial lines where we're actually trying to get this out into the world. If you've decided to file for a patent, if you're actually given that consideration, then people talk about where do you manufacture it or where do you sell it. Quite frankly, in the photonics world, looking at the benefits, cost-benefit analysis, I would think about filing a patent in Europe, the United States, China, Korea, and Japan. And if you've got those 5 countries, the IP5 as sometimes we call it, you're going to actually have got the best protection that you would get, because anybody who doesn't manufacture or sell in at least one of those countries is actually going to not be able to make a decent business at all. So I hope that answers your question, Jose.
It does, but also I realize that if I ever want to start a company, I have to save a lot of money for IP protection. I have a question from Jimena Garcia Romeo. Hello, Jimena. Hola. When do you think it is advisable to implement a trade secret protocol?
Jimena, I think that's an excellent idea, and I would say that any company involved in manufacturing needs to have some form of protocol engaged with it. And it can be as simple as obviously just having non-confidential disclosure agreements in place with all of your staff. It could also involve non-compete. What we mean by non-compete is your staff members cannot leave you and go to another company. Research institutes and universities slightly different on that, but for commercial companies that can be extremely valuable, and it can go as far as having certain degrees of knowledge. So the people involved in the core technologies are limited to a certain number of people, have non-competes. Those outside of that broader area are able to use, have much more access to it, and maybe don't have non-competes. But it also means, to a certain extent, at least in commercial companies, also monitoring publications. I think it's great doing publications, and I think more scientists and engineers in commercial companies should be encouraged to do that. But you do need to make certain that you review a lot of this disclosures that people are doing before it goes out, just to make certain that nothing slips out of the door. So to answer your question, always have one. It depends very much on the level of depth that you want and how much you actually want to keep in-house as to how detailed those protocols are.
What I'm seeing now also from the European Commission a lot is not only on the high TRLs, on the pilot lines, but also on the low TRLs, even in the FED open proposals, that people already from the very beginning, they have their data protection already planned. Is that right, John?
Yes, indeed. It's something we insist on now, that there's actually a credible plan as part of the research proposal, because it's very important for people to start thinking about this right from the beginning, even if it's a bit of a mindset change for some of the researchers.
It is something that I have seen a huge paradigm shift in Europe, Robert, and also everyone who listened to this presentation. If you ever had the chance of having a cup of coffee with Robert at any conference, it's a great experience, and he's the one who will maybe guide you in the case-by-case scenario. He's guiding many of our members. So, Robert, I consider an honor to have you as a friend. Also, I consider an honor to listen to that great presentation. We move to the next speaker, and we go to a person who I see.
Thanks, Jose.
Before the COVID-19 time, I used to see Scott Jordan more than my wife. We were all the time traveling around the world. Now we are confined in these walls. Scott also is a representative of photonics at PI. And in this time, the tragic coronavirus epidemic now drives sudden urgency for flexible and rapidly scalable contract manufacturing worldwide. Whereas costs were an original attraction for manufacturing in China, costs must increasingly be addressed through automation and innovation. By developing and demonstrating proven scalable approaches to photonic device manufacturing automation, the EU's photonic pilot lines take on new importance. However, packaging costs remain dominant, and repetitive, time-consuming alignment processes rank over all other cost contributors through the test and packaging chain. Innovation in the form of fast, automated alignment micro-robots reduces this cost by 2 orders of magnitude, enabling our industry's response. Scott is the best person to help you with the automation, alignment, and fast alignment of photonic devices. And I would like to invite the people in the audience to go to, in November, to the EPIC Automation for the Packaging and Testing of Photonic Devices event, which will happen at the headquarters of Physics Instrumented PI. Scott, thank you very much for being with us this afternoon. Your presentation is about to be seen by hundreds, I think thousands, tens of thousands, millions of people. Thank you very much. The floor is yours.
Thank you, Jose. Thank you for joining us here today. This is Scott Jordan from PI, talking to you from California. This is pre-recorded, but I am attending the online summit and I hope that we can interact via chat while we are here together. I'd like to talk today about the pilot lines and the role that they are playing in the world's recovery from the coronavirus. There's a lot to unwrap here. Let's just get started. We'll start with a review of how we got to where we are, why the pilot lines exist in the first place. In the Photonics 2021 initiative that was published in 2013, 7 years ago, there were proposals for a series of pilot lines, each of which would serve as a template for the cost-effective best practices manufacturing of particular types of component devices or photonic devices. This has been successful. We now have these pilot lines established. And as you can see from this article, Europe's resilience in the global photonics marketplace, these pilot lines are regarded as enabling high-tech small and medium enterprises in Europe to take their good ideas, scale them up, validate them with customers for commercial production. Well, this has been successful, but maybe not successful enough because there's still a great deal of dependence on China, both for low-cost manufacturing and assembly, contract manufacturing, things of that sort, and also as a major consumer for these devices, but also for some of the raw materials. China today dominates 97% of the rare earth oxides that are mined in the world. They don't have 97% of the reserves, but they have 97% of the active mines because China is very good at doing these things at low cost. Some of that has come back to Europe in terms of investment, including research investments, such as $3.4 billion to Sweden in various research applications, 2018, Luxembourg, 1.6 billion, and so on. So this is perhaps a risky situation, as we may have seen with the advent of the coronavirus and also the trade tensions, the trade wars, the sanctions, all of that that's been going on in the past several years. Perhaps being so dependent on China is not such a great idea. Maybe we need a more diversified set of geographic supply chains. So let's talk about that. We're starting to see companies that do contract manufacturing and assembly in China starting to look elsewhere. I have had conversations with some pretty big names in the contract manufacturing industry about new operations that they're considering in places like Brazil, Mexico, and some of the lower cost countries in Europe. So I think that this is a trend we are going to see. It has a name. It's called decoupling. And you will find multiple news articles and analyses that mention the term decoupling as a strategy that many industries and manufacturers are exploring to reduce their dependence on China. So pilot lines play a role in that because they help us, our customers, the people in this room, and they help us establish best practices for building and manufacturing these devices. And one of the things that the Photonics 2021 initiative identified was the new need for new concepts for economic packaging and assembly. And the reason that's important is because packaging is so very costly. If you look at the graph on the right-hand side of the screen from IBM, you can see how photonics absolutely is dominated by the costs of packaging devices. An earlier analysis in the Journal of Lightwave Technology showed that the the various costs that go into packaging are distributed as you see here, and the ones with the red arrows are those processes which are dominated by alignment, the need to take photonic devices and bring them into close proximity, maintain submicron scale alignment during the bonding process. This becomes more painful and more costly as the devices grow more complicated with more elements, more channels, more inputs, more outputs, all of which need to be optimized in more degrees of freedom. Traditionally, the way this has been done has been through lengthy sequential loops of alignment sub-processes where you'd align one device, then you'd align another, and that they would interact in some way, perhaps geometric, perhaps optically. You would have to go back and realign the first device, and so forth and so on. The more complicated the device, the more of that you have to do, and the more painful it would be. Until now. Our contribution. First, we make positioning equipment. We're known for our nano positioning equipment, our micro positioning equipment, our 6 degree of freedom micro robots. But in recent years, over the past 5 years or so, we have been building in intelligent algorithms that allow multiple complex alignments to be performed in parallel. So in other words, if you have an array input with multiple inputs, multiple outputs, you have perhaps multiple elements, and everything needs to be aligned in multiple degrees of freedom, we can do all of that in as few as one step instead of lengthy loops of multiple steps. So typical alignments that used to take several minutes to perform, we can now perform in a second or two. So it's a significant, about a 100-fold improvement in throughput. That's a very key new concept that is being leveraged by a new generation of tool manufacturer. It's building capital equipment for people who manufacture the photonic devices, and for their contract manufacturers as well. Two that I would like to specify here, or like to spotlight, is one is in the center, the upper part of the screen. That's Form Factor. Form Factor makes wafer probers that have been enabled with photonics using this technology that I've described. So here, for example, you see an edge coupling situation with an array input and an array output, some electrical connections, and the chip is being aligned very rapidly so that the testing that probers do can be performed economically. Now, in the lower right-hand corner, you see another video from a company called Tegema in Eindhoven that manufactures a new class of tool, radically new concept for tooling that is so much faster. It's about 10 times faster than conventional tools for packaging and assembly of photonic devices. It also takes up less floor space, so you have savings upon savings. So I think these fulfill the vision for new concepts for economic packaging and assembly that they were talking about for the 2014-2015 timeframe. And here we are, finally available. So, confronting the global challenge, to go back to the 2013 Photonics 21, the goals there were to improve the infrastructure for photonics manufacturing, establish public-private pilot production facilities for industry and research institutes, that's the pilot lines, and to reinforce the innovation ecosystems at local and European levels. And as you can see, there's a lot of significant, meaningful innovation going on. This is good news for the world as we attempt to branch out beyond China to build our devices and in other low-cost venues around the world. Now, I hope we can discuss with you your needs, your applications, what you want to do, where you want to do it. I am available here in the online summit via chat, and also feel free to reach me via email, WeChat, LinkedIn. We have a tech note describing how this parallel technology is actually implemented, and it's actually pretty straightforward, easy to use. I look forward to talking with you about that. Stay well, everybody. Bye-bye.
Thank you very much, Scott, for a great presentation. It is so great to see just the picture of your building in Karlsruhe. It's just such a beautiful area. Well, first of all, you have been playing quite a big role in the pilot lines because you have been engaging a lot with PICSAP, and I want to engage you a lot also with the fabulous pilot line because I'm going to tell you about my passion for micro-optics. The reason why I have a huge passion for micro-optics is that, you know, right now we are actually enabling technologies in Europe very unique to make wafer level low cost. But micro-optics by itself is something as very beautiful but small and useless as you can think. It has to actually capitalize from something. So what I have been seeing is a lot of micro LED manufacturers, big cell manufacturers, LED manufacturers approaching us and wanting us to make micro-optics at wafer level. How have you seen, in your opinion, for the micro LED and for the big cell market? How have you seen this growing, and what kind of questions are you getting from your customers on this?
Well, first there's a wafer level component to micro LEDs and display technologies of all sorts, the micro optics and so forth. The folks at SUS Micro Optics in Switzerland, in Neuchâtel, they are doing some very innovative work with wafer level optics, many applications ranging from automotive to virtual reality displays and things of that sort. So that's something very exciting to see. We see operations from innovative companies like Sony, for example, and clearly the folks at Philips and folks of that sort are pushing those technologies very hard. On the demand side, we see continuing escalation for small portable devices that require these technologies as they emerge, ranging from the next generations of smartphones to the virtual reality technologies that are coming to market, wearable devices and things of that sort. Each of these depends on driving the volume up and the costs down, and that is impacted by yield as well. It all needs precision assembly, it all needs testing, and everything, every step in between. And that's what excites me personally, because precision positioning and the need to keep these things aligned during the assembly and test process that's always been the pain point. And that's what we have solved.
Indeed, and one thing that we also, in the silicon photonics, photonic interdiscrete indium phosphide, one thing that we are seeing is that there is a big paradigm shift coming. So the 400G, we worked really hard on it, we got it, we did it, and now they say, now we need something else. And there's a big unknown on what is this thing that we need, and we are discussing with many different partners, but it is clear that there is something low cost, and there is something that can be packaged at wafer level with co-packaged optics, and it has to have a very easy solution for the fibers. How are you positioning PI to help the companies on this?
Well, there's one thing that I wanted to interject into all of that as well. We also see new technologies, new paradigms, new lane changes coming. Quantum computing is one of those things. It's already big business for us. We have multiple customers here in the United States. It's significant business. But I would like to call everyone's attention to a recent paper by Ray Chen of the University of Texas in Austin and his colleagues. They have demonstrated a arithmetic processing unit implemented in photonics. Now it's I believe it's a 4-bit processor, so it's just a start, but it's operating at 20 gigahertz. Now think about that. Think about what the fastest GPU and fastest CPU you can purchase today for any purpose, for any amount of money. And this is 10 times faster. And it's an all photonic implementation. This field is going to get very interesting. And we will rely on the pilot lines to show the way and how to implement the manufacturing of these devices as they emerge.
For all the people in the audience, you have an alignment challenge or you don't know how scalable your packaging idea is in the volume production, I recommend you to have a cup of coffee with Scott Jordan at any of the conferences. Just look around, he's always there, like me, we're always there. Thank you very much, Scott, for a great presentation. I very often get the chance to introduce a speaker. Rarely I get the chance to introduce a chair lady. Thank you very much, Francesca, for being at this session. Francesca is the laser expert at EPIC and also the main contact person at this moment for the MedFab pilot line. Her passion is to help companies that are making innovative products into reaching markets. So Francesca is going to take care of the rest of the session. Francesca, the floor and the attention of everyone. They're all my friends. Treat them nicely. They're all yours now.
Thank you, Jose, for the nice introduction and for co-moderating so far with me. And with all this, thank you to all these fantastic people here. Also to Scott to presenting now the last talk. So if we don't have further questions, maybe we stick to the agenda a bit, and so we can go on with Peter Dumont from Luceda Photonics. So Peter Dumont is co-founder and CTO of Luceda Photonics, and he obtained his PhD in electronics engineering from Ghent University on silicon photonics wavelength filter devices. Then he moved on and he went to the coordination on APIC's Fab, the European Silicon Photonics platform, which he grew to a partnership offering MPW, packaging, training, and design services. While working on the IMEC Silicon Photonics platform, he implemented many PIC designs and co-developed IPKIS. In 2014, he co-founded Luceda to support the growing user base of IPKIS on a commercial basis. So now, today, we will have him here talking about engaging in PIC design. So now, Peter, the floor is almost yours. Now.
Engaging in photonic IC design. The number of photonic IC technologies and applications is growing tremendously today. Design automation software allows you to design and simulate your photonic IC and that you're developing and take it from an early stage prototype all the way to production. In this talk, I'll show you how you can engage with the design of photonic integrated circuits. Let's first have a look at the ecosystem. PIC technology is really abundant today. There are a wide range of foundries around the world, in North America, in Europe, in Asia, and with technologies ranging from silicon photonics to silicon nitride to indium phosphide and more. There are also an increasing number of companies which help you with the packaging and assembly of photonic devices. Hence, there's a lot to explore if you're looking to scale your application to a photonic IC. In Europe, we've also set up a quite strong R&D support ecosystem in place. There are pilot lines offering newer technologies to novel application areas. There is Europractice IC service, which offers somewhat more mature technologies. There's ActFast, which gives, especially to SMEs, a lot of innovation support, and EPIC's Fab organizes a range of trainings throughout the year in order to build up your workforce. When we look at the design, we see that our customers build microsystems from a variety of technologies in a very hybrid way. For instance, they even combine silicon and indium phosphide chips on a single carrier platform. Both the PIC and the assembly is important. And your foundry relations, the management of that is very important. And when we look at the details of the design, we see that even though foundries tend to offer an increasing number of pre-validated building blocks, still more than 80% of the design is, I would say, very custom, from the small building block all the way to the full circuit. Why is that? Well, simply because the number of applications and specifications are so wide that a single technology can never meet all of these in one platform. Hence, it becomes very important to consolidate the knowledge and the IP that is developed within the design team and be able to reuse it across people, but also across projects from one project to another. Let's have a look at a small example. Here is a screenshot of a chip designed by Lucida for a space application, an R&D demonstrator. And what did it do? Well, we took silicon photonics technology from CA Leti in France. This was actually offered through CNP, a broker in France, which is a member of Europractice. We looked together with PICSAP, the packaging pilot line, at, okay, what are the rules so that we can properly package this chip later on and make sure that a fiber array can be attached, that we can put an on-chip thermistor on it for temperature management, and so forth. We took several PDK components, which were pre-validated by Leti, for instance, high-speed Mach-Zehnder modulators. We also developed our own custom components, and we developed complex parametric subcircuits, AWG circuits, Mach-Zehnder filters, which were necessary for this very specific application. We also took assembly rules and blueprints into account. So you see that you have to bring together quite a number of different aspects, and there's a lot of custom design. So what we teach our customers is to really use an internal design kit model, we call it. Our design teams typically take one or several foundry. They take assembly design kits or rules. They may even take third-party IP, such as from a design house. And then on top of that, they start building their own design kit, their own design library, which consists of their own cells, their own routing algorithms, their own macros, their own interfaces to electronics, to fluidics, and to what's not. And it's important, of course, important that they do this in a way that they can reuse all this embedded knowledge. That they assure the quality, there's proper revision control, and so forth. And that brings us to the central vision of the IPCIS software platform of Lucida, which is that we think all the different design aspects from circuit design to PDKs to device design to validation of devices and circuits need to be tightly interlinked in one coherent design flow. And this is what our software enables with a very high degree of automation. Let's have a look at some of the details of that. Let's say, for instance, that you have this kind of splitter here. Well, what you do with the software is to automatically export 3D geometry of this splitter to a simulation tool. In this case, give the example of export to numerical FDTD, but you don't only export the geometry, you can also, in IPCIS, in Python scripting code, encode the simulation recipe. And these simulation settings will be exported together with the geometry to the simulation tool. After the simulation, the simulation results are gathered and imported back into IPCIS, and a model is fitted in an automated fashion to it. In this way, you can fully close the loop of automation on the device level. And there's two important keywords there: automate whatever is possible, and remember the recipe. You can take this to a next level and develop fully parametric models. For instance, directional coppers as a function of gap, width, and so forth. Once you have these very powerful models, you can actually start to use these for device installs, as I will show later on. One step before that is to start composing subcircuits from individual building blocks. Well, again, there is a code-based approach to do that, based on simple specifications in Python, like place, join, and so forth. You can compose subcircuit layouts. And very important and essential to a properly organized design flow is that this can be fully parametric and fully hierarchical. And not only do you obtain the layout of the circuit, automatically IPCIS will also extract a netlist and the simulation model of the full subcircuit for you. And that's very, very powerful, because now you have your specifications, you have your layout, and you have your model all linked tightly together. You can then take this and stack it into higher level circuits and not only perform the layout, but also simulate the transmission or other characteristics of the device in frequency and time domain. Our customers can then take this one step further, and in their own design libraries, they can create powerful macros where they can go all the way from specifications, for instance, center wavelength, free spectral range, roll-off, and so forth, and based on their components, on their routing macros, on their model extraction methodologies, for instance, they can synthesize the devices necessary and use it as part of their chip design. One other example of that is our own Lucida's filter toolbox ABLG, where very similarly you can go from ABLG specifications, free spectral range, center wavelength, and so forth, all the way to a laid out and simulated ABLG with its circuit simulation model available. So based on all this infrastructure, foundry PDKs, of which there's a lot, very far design automation, predefined libraries with powerful components, customers can really create their design macros, doing complex things, do this in a relatively simple way. This requires an engineering methodology which is suited for this purpose. And what we train our customers on is to really start thinking of design IP and creation of design IP like very similar to a modern software company making software. This allows them to gain a lot of productivity by, again, automation and encoding recipes in code. My colleague, actually, Martin, will give a talk at the PIC conference going into much more detail about this methodology. So I kindly refer you to that. So in summary, everything is there. There's a lot of PDKs there from a variety of foundries targeting a large range of application areas. There's packaging technology, there's design automation for you to create designs for your application.
Thank you very much, Peter, for your contribution. So now we have Peter here, so we can ask him all the questions we want to ask. So Peter, can you hear me? Peter, you might be unmuted, so muted. Okay, so maybe we have some issues with the microphone, Peter.
No, I'm there. Can you hear me?
Okay, there you are.
No, I was not muted.
Okay, weird, but we couldn't hear you, but now it's all perfect. So thank you very much for your contribution. So I would like to ask you, because we see here today a lot of some of the pilot lines you mentioned, but we don't have act fast. Can you maybe give a bit to our audience an explanation to how actually Act Fast is acting that is a bit maybe different than the usual other initiatives that we have here as hosts, and maybe they can get to know better to what the Act Fast can do?
Oh, a very good question. Well, I'm not a I'm not responsible for ActFast, obviously. Maybe indeed they're missing here a bit today. They're a bit earlier in the chain, I would say, when you look at the technology readiness levels. If you're really as a company, especially as a small or medium-sized enterprise, if you have an innovation problem, and maybe you're not even in the optics field, but you may think that, okay, maybe I can scale down my application by using optics, and integrated optics is just one of the possible solutions, of course, micro optics and others are as well. then Act Fast is an EU-funded project, in fact, or activity with a very wide network which can support you in this innovation problem and guide you to the correct people who can help you. And the pilot lines are one of the solutions that Act Fast can also point you to. So it's all connected in one way or another.
Yeah, that's good. That's exactly the key point. So it's maybe serving a technology that is not mature yet, or that it doesn't have experience in photonics, but is all connected. So that was the good thing I wanted to hear. That anyway, ActFast is involved in all these European initiatives, and so it's really good to have the opportunity to, even for non-experts in optics, to be brought into the photonics and into the pilot lines that actually are already then expert and can help you this technology. So this is good to know. And this was enough. I didn't need any details. What was exactly what just the idea behind it and the strategy behind it to support also the present pilot lines here at this session. So I do just would like to remind you that also for the attendees it's possible to ask questions. And if you were not instructed or if you forgot, you can always ask questions in the chat, and you can also raise your hand. And also, of course, this is valid for our panelists, but also for all the attendees that are offline, let's say online, but still hidden in our room. So if maybe we stay again in a bit on time with our schedule, so we can go on with actually the next talk that is from Kevin Williams. So full professor and chair of the Photonic Integration Research Group at Eindhoven University of Technology. So he will present today the JAPIX pilot line. And so in his case, the European Commission Manufacturing Pilot Line, this JAPIX is a project for photonic integrated circuits, and it's in the indium phosphide pilot line for upscale, low barrier, self-sustained PIC ecosystem. Indium phosphide photonic integrated circuits PICs offer game-changing performance capabilities across multiple market sectors. And the JAPIX pilot line is the European Commission Manufacturing Pilot Line, which puts in place the technological and operational processes to accelerate the uptake of PIC technology in new markets, align scalable and interlocking services and value chains, accelerate time to market with predictive design for fewer and faster design cycles, and offer foundry processes at TRL7, so pretty high, and sharing process optimization across products. So please, Kevin, I assume you want to go live. So you should have be present now and share your screen.
Okay.
There you go. Yes, we see now. If you go to presentation mode, would be perfect. Perfect. Thank you. Then, Kevin, the floor is yours.
Wonderful. Thanks very much. I'm feeling slightly brave doing it live, but hopefully it works out. So thank you for listening to this presentation on the JAPIX pilot line, and specifically on indium phosphide integrated photonics. I'd like to talk through what we're doing within JAPIX. I think we're reasonably well known in the PIC community for technology orientation, the deep dive trainings, the roadmaps, the technical notes. Many of you on this call may have been aware of the MPW services that have been running for some years now, prototyping, MPWs, PDK support, templates to accelerate design. What we'd like to talk about today is the pilot line. And pilot production for us is learning how to scale, learning how to manufacture. So this is about design for manufacture. It's about getting known good die to the customer. It's about automating the processes, scaling the processes. So doing everything in a way that scales for volume. We also have some initiatives that I think are worth being aware of in manufacturing innovation, looking at new types of technologies to improve yield, to improve performance in the future. I'm not going to talk so much about that now. That's in a separate program. I'll focus on the JAPIX pilot line now. So the way we achieve this, the way we reach out to many market sectors is through a building block approach. One platform technology, one wafer scale technology with many different capabilities on board. We have lasers, amplifiers, grating technologies, detectors, modulators, passive components for building filters, combiners, And we're also introducing polarization components as well. So quite a broad range of functions. And those of you with PIC experience will understand you can build quite a wide range of functional circuits with this approach. Give you a flavor for that with some of these recent highlights. So on the left, we have WDM chips from 3 different fabs. We've got fast Mach-Zehnder modulators. We have tunable lasers on these chips, DFB lasers, splitters, AWGs. So quite a rich range of components and high performance components as well. So we can do transmitters for the telecom market. We can also do sensor readout circuits. You see that in the middle. This is designed by Bright Photonics, for example, on an HHI platform. And you see cascaded AWGs with 100 detectors on there. And on the right, it's blocked for me, but hopefully some of you can see it, a wide tunable laser on the Smart Photonics platform. And that was tunable over about 100 nanometers. So quite high performance components. And I'd like to draw your attention to a couple of recent special issues in JSTQE at the bottom there, where some of the prototypes have been published and peer reviewed by the scientific community. So that's what we can do. This is the sort of performance we're looking at. They're just snapshots, so I'm not trying to summarize everything, but we have the high-speed modulators. These particular examples on the HHI platform, where we have EAMs at 56 gigabaud. We've had a comparable result as well on the Smart platform. Recently released, there's the 100 gigabaud components for Mach-Zehnders from HHI, and there's the precision multiplexers, which are enabled by scanner lithography at Smart Photonics. And the nice thing about this is that it's really making things reproducible and also bringing the performance up with excess losses dropping to half a dB, for example, with an AWG. So really quite high performance components. I'd like to talk a little bit about what we're doing in the pilot line now. So there's four phases that I want to address. And the first phase is really design acceleration. How do we get to a manufacturable PIC design quicker? You've heard a little from Peter, very important work going on at Lucida and other companies of that ilk, developing the design methods. The CAD tools are being improved and integrated with electronic design tools, such as Synopsys, for example. So you can design your circuits. We see increasingly powerful compact models, so we are more predictive in our design. Very important to our platform is the process design kit. So here we're separating out customer IP from foundry know-how, from software know-how, and even from IP vendor know-how. So making clear distinctions in a software interface. And we find that very powerful because the customer makes conscious choices about how the customer is choosing to share IP or keep IP. Now, clearly it would be more complex than that if you start interfacing with professional designers, but it's the customer that decides. And on the right, a couple of images to give a feel for the new IP blocks that are emerging. You don't have to invent your own AWG every time you want to create a circuit. You can license them. There are software companies out there, such as Bright Photonics, that would do that sort of thing for you. Design services from Bright or VLC that can help you accelerate your design if you so wish. So that's one part of design. Of course, there's aspects of it to make it more and more accurate. So I'd like to touch on those now. Production is where we need to put a lot of attention. We're looking at design agnostic processes. So we've got many tens of designers active, trying to create very different types of designs, and they're expecting different things out of the same building blocks. So we need to be able to process using the same process technologies if we're going to accelerate the learning, the yield learning. So the PDKs help us with that. Increasing the amount of measurement and metrology helps us with that. So this generic approach is accelerating the yield learning across all customers, whether they're doing MPWs or whether they're doing pilot production at wafer batch, multi-wafer batch scale. At the moment, our PDKs are supported by, offered by 3 foundries through 10 or more software vendors. For us, the pilot manufacturing is very much about using the same methods as you would at manufacture, at volume manufacture. So everything we're doing here has to scale. Wafer scaling, batch scaling. And this applies to test automation as well. So we put a lot of effort at the moment into high throughput measuring. Here you see an image from the PhiContech tool that we're jointly developing with the PIC pilot line. The focus here is accelerating the test so that we can get 3 sigma and beyond for important key design variables, so that we can do manufacturing grade PDKs where the customer knows exactly what he can expect in terms of yields. And also we want to be enabling test as a service, and we want to be enabling known good die selection. So there's all sorts of methods being developed so that the customer can very much define how the test is fulfilled. Additional to that, on the right, you see a recently launched test board, evaluation board from HHI. You can see a little bit about that if you follow the link at the bottom. What we're doing here is trying to support labness businesses when they're just moving into the fields, trying to work out whether get fast feedback on the performance of these chips. So it's quite a powerful tool. You don't need to buy racks and racks of equipment to be checking out whether or not your components are working. And this again should help accelerate the design cycle. And within the program, we're also looking at validation. So we're validating with sensor technologies as well as communication technologies. You can get a feel for the scope of work that we're doing by going to the website. As I highlighted at the start, there's 2 ways we're working at JetPICs. One is the PIC prototyping. That's people getting into the business, trying to work out how to make PICs work for them. The pilot line is the next step beyond that. Pilot line is when the customer has made this decision. Yes, I've got a valid prototype in the lab. This is working for me. Now I need to know how to manufacture. And that's what we're working on now, and we expect that to launch within the next six months or so. So we'll be very keen to hear from you if you have interests in that. Final slide is really to acknowledge the many businesses that have been involved in this. In the middle, we've got the JetPICs pilot line partners, but also there are many beyond the pilot line that are enabling much of the work we're doing. Thanks very much for your time.
Thank you very much, Kevin, for your contribution. So now we can unshare the screen.
I think you have to do that, don't you?
Now you can do it yourself as well. Okay, yeah, very good. Yeah, it's for both possible, but I am not sure if I have this power, but probably yes. Thank you. So thanks a lot for your contribution. So what is for us maybe here important to do, considering that we have many young, old, and middle-aged pilot lines, is also to learn from each other. So this is a bit the idea behind it, in my opinion. So as I saw, so JetPICs is running now since 1.5 years, right? So yeah. And so it would be nice to share something like a lesson learned. For example, you mentioned that you have 3 foundries working together for JetPICs. And so do you have something to tell us about how you can actually coordinate these 3 foundries, if there were issues and that you overcame them, or something like a good examples that the young pilot lines can learn from that are here in the room?
I think that's a hard question. I think we're working in a slightly different way. What we're really trying to establish here is an industrially viable framework. So, the idea of coordinating is not quite right. What we're trying to do is make interlocking products so that the customer really gets what they need, and there's a sustainable model behind that for the suppliers involved. And that will be slightly different for different partners. We work with 3 foundries because we want second sourcing. We want that richness of offer. So there's not an intention to make a homogeneous offer here. We want a rich, industrial, sustainable model.
That's a good statement. Definitely a good way to say why you have three and how you can not coordinate, maybe manage them. What is the right verb for that?
I think they perfectly well manage themselves. They don't need
exactly.
What has been a problem in the past, I think, is really linking up those powerful design tools, those powerful test environments, getting those validations out into the market. So that's really the role of the pilot line. The manufacturing, the foundries can do that. They're doing their own good work on that. So yeah, it's an alignment, if you like.
Yeah, that's a good also, even it's a good pitch, because validation is important for you and in many pilot lines, but I guess for our next speaker is even more challenging because it's about the medical devices. Ooh, so it's really, thank you very much, Kevin, for your contribution. If you can stay here longer, we can maybe listen from your, maybe answer to you or from other speakers from your experience. So thanks a lot for being here and then staying a bit longer also with us. Because now is the time to a newbie. For a newbie, our newbie is MedFab. So MedFab is presented today by Robin de Bruin from Philips, so Business Development Director at Philips Innovation Services in the Department of MEMS and Micro Devices at Philips in the Netherlands. So MedFab will serve as a European first pilot line dedicated to manufacturing, testing, and upscaling of new photonics technology for medical diagnostics, enabling accelerated product launch. And basically, that's the issue already that you hear. So MedFab will bring the high quality infrastructure and extensive know-how within easy reach and of the SMEs and other European industry. Globally unique feature of MedFab is its operation in medical domain, setting requirements to meet regulations, that is the and the competitive differentiation in the seamless operation between ISO 13485 certified companies and RTOs, when single entry point can serve SMEs operating at different TRLs. So professional customer interface will be operated by staff with extensive experience in the field of medical devices. So today, Robin is here, so I really a pleasure for me, because as Jose introduced at the beginning, we are EPIC involved in Robin, and I am the responsible person, so it's really nice to have you here, Robin. So please, the floor is yours.
Thank you, Francesca. What a magnificent summary, what an introduction, thank you. Nobody could have done better than you, and we truly love the collaboration with EPIC. Thank you for that. And maybe to you all who's thinking, is Gandalf presenting on MedFab? I'm sorry, the hairdressers and lens had just opened. I have my appointment on Saturday, and afterwards you'll recognize me again. So introducing MedFab, I'll try to share my screen here. Sharing, let me know, Francesca, if it's working.
It's working, but it's still not the presentation. Now it goes, perfect. Yeah, Robin,
there we are.
There you're all.
Thank you, thank you. So I'm from Philips Innovation Services presenting on MedFab, as we are not the project coordinator. Project coordinator is VTT, but we're in a unique position that we have a front office, because we are a very open pipeline, and I am leading that effort on opening the front office, and in that position I'm presenting on MedFab. So why MedFab? As Francesca said, we're a newbie. We just started, and we're establishing our goal. And I'm here to present on that and the advancements that we have made now. So the reasons why MedFab was started is that we see a lot of development, product development lacking in the medical devices using photonics. And there were two reasons actually for this. One is that there's a lot of fragmented offerings in the photonic field and in the medical device field. But also secondly, that regulatory compliance is highly demanding, especially for SMEs, mostly the companies launching and developing these products. So there was a high need for a pilot production line to accelerate this medical device product development. So we are dedicated to efficiency. So what distinguishes us from other European photonics pilot line is that we offer a low barrier open access model. So the real purpose is to dedicate to medical devices, but be open to all product developments out there. We are a consortium of 18 partners from large industry, RTOs, ISO 13485 certified companies, and we aim at reducing the R&D costs for these SMEs developing medical devices, as there's so much experience and installed base of all our partners. We think we can do that. And as I said, we're truly open. As here's the email address, info@medfab.eu. If you have a need for accelerating your development, you can email it, and you can be assured that your order or your request is channeled to any of the partners that have the best capability of handling your request. And we don't have the front office open yet, but I can assure you that we are already in line to take in requests, and we have several already running for that. So in this establishment phase, as Francesca said, it's very important to validate such a pilot line. So we have many application areas and users identified, from hospital to home care to also diagnostic platforms, where we validate the technology of the pilot production line. We have in the hospital environment solutions to assist doctors by giving real-time information on the treatment if the treatment is progressing without the need to send patient samples. In home diagnostics, we can use it for monitoring how a patient is recovering from an operation or a fit of illness and getting a wider picture of the situation than currently possible. Molecular diagnostic is about establishing a clinical picture or diagnosing an infection based on serum, saliva, or urine sample. So these are some of the examples that we're working on, and progress of them will be reported during the whole pilot line. So the technologies that we have available for diagnostic device, but also treatment, can be quite diverse. And in the R&D phase, up to the ISO 13485 certified manufacturing, we have a wide array and a wide toolbox of different technologies. Fiber optics, microfluidics, service functionalization, instrumentation, optoelectronic integration, miniaturization, also a large part micro-optics. I will not talk about micro-optics because our good friend Rolando will be after me, so I'll not steal his thunder. So we will offer all these technologies in a photonics model integration, looking at packaging, and also developing disposable in vitro optofluidic diagnostics. Oh my God, there's so much words here. So any combination of technologies that might be useful for your product is available, and there will be a seamless integration from R&D up to the manufacturing. So what is our offering? I've talked a lot about applications and technologies, but the core of MedFab is really the customer position. We allow you to interact with all the MedFab partners from development up to upscaling, and this means a lot of work for us. As JEPIX also presented on their model for collaborating between foundries, we aim to set up a pilot line of collaboration between R&D, between manufacturing, between technology blocks at one partner and technology blocks to another, seamlessly aiming to seamlessly develop and pilot produce the medical device up to pilot production and clinical trials, which is necessary for medical devices and a very big step in a product development in the medical domain. So the philosophy that we handle all the requests and the applications that we're working on is based on not only on technology readiness level, so not only the maturity of the product, but also the manufacturing readiness level. As we see a lot of these problems originating more from the manufacturing than from the technology readiness level, or let's say there is more known about technology readiness level and less about the maturity of the manufacturing process. We use this chart to investigate where is a technology or maybe a prototype product, and how can we accelerate that up to the top right partner where we develop, launch, and also maintain a product while it's in the market. As you can see, most efforts would be from RTOs would be into increasing technology readiness level, but industry playing more on the right side at more mature manufacturing processes and trying to mature that. And there's a gap in between that, and the philosophy is that we will provide this overlap and cross that bridge. So the single entry point, as I mentioned, we will be setting up a front office for professionals in the medical domain. Minimize this. Professionals in the medical device domain, where we can interact, and there will be information shared only on a need-to-know basis, and we'll be setting up NDAs on basis of customer request, so every information is handled prudently. So the customers we're aiming for can be both in vivo and in vitro medical devices, and from small to large customers. And as you can see, the whole of MedFab is within the dotted lines, where there's the front office working with the ISO 13485 certified companies and the RTOs. But there's also interactions with other European pilot lines, as you just mentioned, for micro-optics. We also have some partners from the Fabulous pilot line in our pilot line. So there's also communication interaction happening there. So a validation program. The goal is that after the 4-year program, we have set up this pilot line, but of course, before there, we have to validate that it's working. So there will be 2 open calls for customers where we can have, enabling the early adoption of the technologies and to demonstrate the pilot line services. And the calls, there will be quite some positions open for customers to call for these for this program. And we invite all of you to monitor our communications to hear when the calls are open. But you can all, of course, the email address is already there. You can already approach us if you have something that cannot wait until next year. So our current status is that we project to establish it starting the beginning of this year. But of course, we cannot operate in a centralized manner at that point in time, as we're now setting up the pilot lines and the technology libraries, etc. But that's why I'm presenting here. We are willing to help the companies. We're here also to network. We're also to learn from you, from the needs that you might have in this pilot line, that we can learn back to developing the pilot line. And so we are setting up a way that we have a very short response time, so that you can be assured that your inquiry will be passed on to the MedFab partners as soon as possible. And each partner will communicate then directly to you independently if that's needed. So the partners, as I mentioned, project coordinated from VTT and other RTOs, Tyndall, Joanneum Research, IMEC, and CSEM. And we, as Philips Innovation Services, are very proud to join this program as one of the ISO 13485 certified companies, together with Jabil and ScreenTech. And we have many companies working on technologies, 3.5 Labs, Vienna Lab, and we have some of the partners for the applications, Stryker, Pola, Renaissance, Antelope Diagnostics, GenSpeed, Anthony van Leeuwenhoek Hospital in the Netherlands, that will provide us with difficult cases to develop a product for. And of course, we cannot do it without the magnificent organization and dissemination of EPIC and Amirs. And I want to have a real big thanks to Francesca and Mariana for helping us in setting up this project. I'm sure that with your help, this will be one big success. So finishing up, as I said, here are all our contact details. We're extremely open. We are here to listen to your comments, to your feedback, to your requests, to your technologies, because our goal is to really accelerate medical device development, and this needs an open communication between all the partners. Not on this slide, it's a bit experimental yet to mention it, but end of this year in December, we had a EPIC meeting planned in Eindhoven in the Netherlands. Magnificent city, of course, technology all around, but also still Corona. But we're solving that, and we expect to be open in December. So put it in your agenda, 8 and 9 December in Eindhoven, medical photonics. So here I finish. Thank you all for your attention. And if you have any questions, go ahead.
Thank you very much, Robin, for your talk, and of course for your great words for us, for Amires, that I also agree is really a really cool partner to work with, and also for advertising already the EPIC event. Robin, I'm speechless. Thank you very much. So the idea is that at this meeting we will have a strong participation of MedFab, and then also of some other maybe possible applicants for the call next year for new projects that can join the pilot line. So it's really a way to meet again also there, like we are here, newbies, so potential customers, but also experienced companies like Philips that is hosting us for learning from each other, and of course to promote photonics also in medical devices. So I would say that we already mentioned that exactly validation of medical devices is not the most trivial thing. So I'm happy that of course Jussi is a great coordinator from VTT, but it's by chance that you are here today presenting the pilot line from Philips side is maybe the best because you are the most experienced one and the one in the work package of validation. So if you can spend maybe a couple of words more on this. So what is the plan, how to support the applicants and also the use cases first, of course. And then if you can say maybe a comment on these first few months of the pilot line, also what is your feeling, or if you have, of course, also questions to the non-newbies, to the oldies, but the oldies doesn't sound good, but to the experienced pilot lines, so please feel free.
Yeah, oh, that's a lot of questions, a lot of things. I think for our position in this is that Philips Innovation Services has been an open engineering company. We've worked for external companies for a long time now, with all the experience of Philips of developing medical devices for 100 years already, and we've gained a lot of insights in how to do that. And it's not something you can write in a book and then publish it. It's by doing that you can transfer this experience, and that's why collaborating in a European pipeline like MedFab is crucial for that. And the open communications are necessary to establish that. And I think coming back to that, if you mention a lot of times medical device is difficult and maybe you scare off, we're also here to give peace. It is actually really possible, and that's the peace that I want to give. Also to other pipelines that might be considering a medical device, just communicate, because we could find ways of making it much more simpler, much more faster than you might have been thinking for now.
Yeah, I guess it can be that this coronavirus didn't have many advantages, but maybe there is so much going on of course, on testing and diagnosis and all the possible companies trying to develop something that maybe is exactly 1 year before the official call, having the great experience and advertisement that yes, we can help you because we have such an experienced partner, and also all the others, of course, also from on the R&D side and from the development of any idea. So maybe if there's something that Corona did good was to promote a bit.
I agree. The impact that it has, that everybody's so aware that this is so crucial to have not only MedFab but all the other companies working in this medical domain. So indeed, it's a terrible crisis, but it has unlocked this field.
Exactly, and also for us is also now in this early phase to also deal with the early customers was also a bit of a push from us to set already the pilot line for this. So if you want to comment on this, of course, not too much, but that actually the things we are dealing basically these first months, I would say this is the returning to my first question. What happened in these few months? It happened already a lot, right?
Yeah. No, indeed. There happened a lot. We had also some requests for technologies using and fighting the Corona crisis, and it has been quite busy.
Yeah, being busy, of course, is good news. At least we could find something to commit ourselves with, and so also for the pilot line for the beginning to accelerate a bit the procedure. So it's definitely good. So, and now I guess if there are no further questions, if there are comments, of course they are welcome. But otherwise, I would give now the ball to the other newbie of the platform. So it's time now for Orlando Ferrini from CSCM. So he's of course, talking about Fabulous and the Fabulous pilot line, being the head of the micro nano optics section at CSCM, and he's also the project coordinator of this pilot line. So I just a few words about it. In recent years, there has been increasing interest in sensor technologies across a wide range of applications. Whilst the industrial and consumer application have driven the first wave of sensor activities, the acceleration of connected autonomous vehicles is focusing attention on advanced sensor technologies such as LiDAR. So Dr. Fallon's presentation shines a light on the key materials development that provide the underpinning technologies that are essential to make LiDAR-enabled autonomous vehicles a reality in terms of both cost and performance. So Rolando is here, but is also recorded, right? So thank you for being here, Rolando, first. Now I prepare I'm not too fast, but I apologize for this, but at least we have some time to chit chat, to say, how are you doing, Rolando, in these days?
Fine, thank you. As you see, I'm at home. We are still partly in home office. And well, we are affected by, like many others, by the situation with COVID. But we are doing well, and we try to push forward as fast as possible. Fabulous.
Yeah, and we will. So now it's time for Rolando, so for the recording, but he's here. So now is the virtual the virtual floor is for recorded Rolando, and so let's go.
Hello. First of all, I would like to thank the organizer for having given me the possibility to spend the next 10 minutes introducing you the fabulous pilot line, so to speak, the new era for freeform micro-optics. I would like to start from freeform micro-optics, introducing the concept, and to explain you what we intend for freeform micro-optics. You are most probably familiar with micro-optics or micro-lens arrays. Just imagine to take a micro-lens array and not being forced anymore to have only hemispherical surfaces, but having the possibility to remove any constriction on the symmetry. Having, for example, shapes that have no hemispherical or spherical shape here, for example, in the middle, up to structures where you lose completely the information on symmetry and you have totally randomness. Why these structures are important? Because there is an actual interest from market and different application fields for freeform micro-optical components. Here on the left, you see a graph with number of publications and patents per year on freeform micro-optics, and you see a clear ramping up. Even in PICs, since here we're talking about PICs, there is interest for freeform micro-optical components. Here, for example, you see examples of freeform micro-optical interconnects that CSM developed in the last couple of years in order to replace current solutions based on collinear, for example, components or bulky optical systems. Our solution is based on freeform micro-optical shapes, either prisms or quarter of micro lenses that, exploiting total internal reflections, can be used as folded interconnects. And this can be produced by wafer scale UV imprint at mass production level. So here, for example, you see the design of these micro-optical components. You have, as I told you, a quarter of micro lens, or for example, a micro prisms. As I said, these components can be fabricated by UV imprint. So first of all, you originate a master. Then once you have the master, from the master, you originate a mold. And the mold is used to replicate onto, for example, wafers into UV curable imprint materials. The first important step is the origination of the master. You can use several technologies. Here, for example, we used 2 types of technologies depending on which shape we wanted to generate. For the Q lenses, we used standard reflow and photolitho, and for microprisms, we used laser microfabrication. Here you see the challenges. If you take microprisms generated by laser microfabrication, you can initially obtain the shape here on the left, which is pretty much good, but have a residual roughness that is detrimental for the optical function. So what you want to do a post-processing, for example, with laser thermal reflow in order to remove the roughness. But as you can see here on the right, at the same time, you lose the shape. This is something that can be, and actually it's being at the moment optimized, but this is still a bottleneck. In order to overcome this bottleneck, you can apply standard reflow, for example, to generate this quarter lenses, with the drawback that then you're limited only to shapes that are residual of an hemispherical shape. We generated these test structures, we made also the optical characterization, and we saw that they're very promising. You can get optical losses below 0.5 dBs, for example, with the Q lenses, but also the mode profile and the angular directivity can be maintained. So they are very much promising for application, for example, in PICs, where you want to connect a fiber with an integrated optical circuit. But again, the bottleneck is how to fabricate these structures, and where Fabulous comes into the game. So what's Fabulous? Fabulous is a European one-stop shop for the manufacturing of freeform micro-optical components. So for example, the structures that you had seen before, and offers you accelerated innovation and production cycles, manufacturing services, going from prototyping to piloting to larger volume production. So it offers you the entire value chain that you can see on the right. Who is Fabulous? Fabulous is a consortium of 19 partners in Europe, funded by the European Commission to build this pilot line. We have two types of partners. On one hand, we have technology providers, those who are providing the elements on the value chain for the pilot line, and end users. We have already 6 companies on board that would like to implement freeform micro-optical components in their products, and will help us to develop the technology capabilities. These are companies like Hella in automotive lighting, Zumtobel in solid-state lighting, Seisenbacher in transportation lighting, Swarovski in luxury, and for augmented and virtual reality, another hot domain for freeform micro-optics, we have Limbach and MicroLED. What provides you Fabulous? Fabulous provides you again the entire value chain for the production services and UV print manufacturing of freeform micro-optics, going from modeling to origination, tooling, materials, quality control, with the possibility of producing these components at wafer scale, roll to plate or roll to roll, and to integrate in products. As you can see here on the right are those, for example, that are addressing the first 6 markets that we have on board already on the project. How we intend to build the pilot line? This is a mission that will last the next 4 years, starting on the 1st of January of this year. We'll focus on 2 points: the setup of the pilot line on the technology level, and the management of the pilot line and sustainability of the pilot line. We do this in different phases. In the first phase, which is the first 1.5 to 2 years, we will accelerate and optimize technologies and processes, and we validate the technology against the use cases. In this way, we'll be sure that we can already serve the needs of certain markets, those we have on board. Once the technology is validated, we go to the next phase that we start during the 2nd year. Will be open calls for pilot cases. What are pilot cases? Pilot cases are companies in Europe, or actually all over the world, that would like to have freeform micro-optical components, and they will send a request to Fabulous for pilot runs. If the request is accepted, we'll make these pilot runs for these companies. This will be very important for us because we'll be using these pilot cases to test and validate the business model. Because we wanted at the end of the project, the pilot line that will be represented by one unique legal entity is sustainable and can survive after the project itself. Why we are doing this? Because if today you are a company that would like to implement freeform micro-optical components in your products, you're facing a big challenge. You have to take all the points on the value chain, scout all players for each point of the value chain, compare them, decide what is the best for you, then also comparing those that can be linked, can be compatible, and at the end you have to build your entire value chain. This is cumbersome and time consuming, and often is a showstopper or a blocking point where companies, they don't have the resources to run this entire value chain building, will stop and not even try to implement these components into their product, missing potentially the possibility of developing a new product, and for the technology providers, missing business. How we solve this problem with Fabulous? Well, we'll have one unique entry point for customers or interested companies interested in freeform micro-optics. And this unique entry point will offer the entire value chain, all the services needed to produce and integrate freeform micro-optical components into products. For whom we are doing this? We're doing this for companies or markets you can see listed here, going from solid-state lighting to day lighting, automotive lighting, augmented reality, virtual reality, security, anti-counterfeiting and branding, optical elements, imagers and displays, consumer electronics, wearables, you name it, you have it. This is not out of the blue sky. This comes from a survey we made during the proposal phase, where we actually looked into our network and started to inquire with companies if they were interested in freeform micro-optics. And actually found there were a lot of companies interested in these new components, and 40, 50 of them already signed a letter of interest for Fabulous, and they will be ready to submit pilot requests as soon as we open calls for pilot cases. With this, I would like to thank you for your attention. I would like to remind you that micro-optics is Fabulous, and I leave it here, my contact details. Thank you very much.
Thank you very much, Rolando, for your recorded contribution. But as I mentioned before, Rolando is here, live with us. So thanks a lot also now live for your contribution, talking about Fabulous. So the question is a bit, let's say, we know that now freeform micro-optics is like booming like crazy. So it's nice that you reported already at the end of your talk that you actually collected this expression of interest from many of these sectors that you mentioned as final user and end users. Do you want to maybe a bit comment on this? How do you feel in this also first few months of the project? Because as we said, you are a newbie as well. How do you feel like that these actually topics are developing? Also, you were present a lot on our online technology meetings of EPIC. If you notice something that is actually going on, maybe more sectors coming in, or even more interest than you'd expected, is it this the feeling? Because from what I hear, is like crazy.
What I can say is that I was extremely surprised to see that there is already a huge interest already. If you remember at Photonics West, we opened the project 2 weeks before, and we're already getting leads and companies that were interested to interact with Fabulous, and it's actually going on regularly. I get emails from SMEs or even technology suppliers and providers that would be interested to partner with Fabulous. What we are doing actually at the moment with our sectoral business developers and the end users that we have on board in Fabulous, we are already analyzing the different markets in order to prioritize the market to address with the pilot case open calls. So we are already, while we are accelerating the technology, we're already, and we are actually creating also the front office, we're already preparing the business ground to be really active since day one when we open the open calls to target the hottest markets.
Okay, so that means that from different reasons, even so for you it was not the coronavirus accelerating the customization and the customer recalls, but still is definitely a super hot topic. So that's good that you are already then preparing, so anticipating as a bit what is happening in MedFab, anticipating what is needed in future so that you are reactive in the right time. And also, then I would like to say, you are mentioning that, of course, a pilot line in general is like basically trying to solve the challenges of other customers that then will apply and then will be helped by the pilot line, in this case, Fabulous. But do you, did you already identify something already maybe in the preparation of the call that is actually the challenge for Fabulous in specific, that you know you have to pay attention, maybe it didn't come out yet because now it's early, but that you are prepared for?
Well, there are a few big challenges. I mean, on the technical level, we have a couple of bottlenecks in terms of origination of the structures or quality control that are known in the field. And we actually expect to tackle them, but also to bring solutions that will be standardized. So we really aim to be a reference for freeform micro-optics in the next years. And we aim also to enlarge the family. We are aiming to have new members on the pilot line as soon as we can qualify their technologies. That's one of the biggest challenges. And from the, let's say, from the functioning point of view, the biggest challenge we know since day zero is the sustainability. This is really our mantra. We will try to find the right business model, also to bring value to the partners on the pilot line so they see the interest to keep the pilot line alive, because the pilot line cannot live without their members. So the members need to believe 100% or 1000% in the pilot line benefits.
Yeah, this is very good point, because it's a thing that you can learn from the experienced pilot lines, but it's also good that you are already thinking about it, so that you don't have the problem at the end that is then unsolved, but already with some business model at the beginning. But now we have also a question from the audience. So I just read it for you. It's from Francois Menard. Thank you, Francois, for the question. So the question is for you, Orlando. So do you find a trend to form freeform optics in the back end of silicon photonics using technology such as grayscale lithography in the silicon oxide top clad of silicon nitride planar waveguides rather than forming them with 3D printing in polymer?
So this is a very specific and technical question. What I can say, well, we are not doing 3D printing in polymer. We are doing UV replication. But to get there, we need a master. So we need an original, and grayscale lithography is one of the technologies we are actually have on board, and we are evaluating and qualifying to generate freeform micro-optical structures. There's no one unique technology that can originate the structures. That's the bottleneck. So each of them has plus and minuses, and we are really, one of the main actions in the acceleration phase is to really understand all the plus and minuses of the different technologies.
Thank you very much. So maybe you can also be contacted offline in case there is more technical questions that has to be asked, because of course we can still connect you also offline if there is some further question.
Francesca, you know that because, and let's say I was reading wrongly the timing of the meeting at 4:30. So the Central Europe summertime, I will have to leave, but people can contact me absolutely offline.
Exactly, perfect. Then we have already the request, the acceptance official from you. So that's really good that we can also offline maybe follow up with the technology that is exactly characterizing Fabulous. But now is the time to go on, so to not be too late with our schedule. So for me, it's a real pleasure to have another epic, famous for epic pilot line. So we have here Sergio Nicoletti. There is actually a director of MIRFAB. So thank you for being here. I just say now I spend a couple of words to introduce the pilot line MIRFAB. So recent developments in integrated photonics components have allowed the miniaturization of mid-infrared spectroscopy, otherwise confined to laboratory usage only. The goal of the MIRFAB pilot line is to open the access to mid-infrared detection systems for companies aiming to integrate state-of-the-art chemical sensors into their products used for real-time monitoring. MIRFAB is truly unique, bringing businesses a broad range of know-how from a variety of organizations, plus a library of state-of-the-art components. MIRFAB customers come away with spectroscopy-based chemical detection systems that meet their specific requirements. The solution on offer combine laser sources, photonic circuits, and photodetectors and analyzer, like photoacoustic detectors, in miniaturized system integrated into standard packaging. They are also cost-effective to manufacture and energy efficient. The intended applications range from environmental monitoring and food quality control to rapid clinical diagnostics. So Sergio is here now, so it's really nice to have you here. But first
Hi, Francesca.
Hi, welcome. Now also live, because I saw you on YouTube on our Epic Online Technology meeting, but now I can also talk to you, so really nice to meet you. And so now it's the time for your talk, so now we can roll.
Good afternoon, ladies and gentlemen. I am Sergio Nicoletti, and I am with CEA-Leti in France. Today, I will present you MIRFAB, which is a pilot line for the development of mid-infrared chemical sensors. If you are familiar with chemical sensing, you might know that optical sensing is a well-established technique for measuring chemical down to the trace level. FTIR, for example, is largely used in environmental monitoring and emission control. However, this technology is bulky and costly and can be difficultly used in applications where the portability is an issue. In breath analysis, the doctor should be able to directly monitor the patient, and this architecture is not suitable for this purpose. With the development of solid-state infrared sources, QCL or ICL, a new class of devices start to appear. This new class of tools, generally identified as tunable diode laser absorption spectroscopy, allows real-time detection down to the sub-ppm level, and in the specific, has a strong potential for deminiaturization. This is the main target of MIRFAB, and many novel applications were recently proposed. Again, as an example, QCL were successfully used to image and differentiate cancer cells in histological tissues. In laser-based optical detection, the source is selected to match an absorption band of the molecule to be detected. Then, either we measure the amount of light absorbed by the environment, or we measure the variation of other physical parameters, such as the local increase of the pressure, as it happens in photoacoustic detection, or the decay time in resonating cavities, as it happens in cavity ring down spectroscopy. The schematic presented here, based on a simple absorption, accounts for detection of gas, but it also working for liquid and solid. In both cases, mid-infrared sensing is selective and sensitive and gives a quantitative estimation of the species to be detected. These are the architectures that we have been investigating with MIRFAB. Going into the details of the project, MIRFAB is in an H2020 pilot line, ending in principle at the end of the year, even if with the current situation we might have an extension. Within MIRFAB, we address both technical and commercial objectives. As technical goal, we target the full wavelength coverage from 3 to 11 micron, which is generally identified as the fingerprint region and where the detection is the most efficient. The technology maturation, where it is necessary, the miniaturization and the standardization of the devices, and the assessment of volume fabrication capability, which is a requirement for the fast taking over and the commercialization of these devices. The adoption of this technology and the commercialization of new devices were among the priorities of this project. We made an extraordinary effort to disseminating and promoting MIRFAB activities, since Europe still has a strong leadership in mid-infrared technology and in optical chemical sensing. Our role was to reinforce this leadership and to make a step forward in the commercialization of mid-infrared based sensing system, either directly within MIRFAB or at the end of the project by the industrial partner of the consortium. The open access to the pilot line service is crucial to deploy these objectives. The approach we are proposing is quite simple. We have a panel of sources, photonics integrated circuit and detectors covering the full wavelength range, and we assembled them and tested in testing devices. These architectures are now available to be customized according to the client needs, and this is the offer that we can make available within MIRFAB. Working together is quite simple and straightforward. We can identify 3 different phases. First of all, we start discussing together to collect the information required to develop the sensor under your specification. Then we develop the first series of modules fulfilling your specification, and then we move forward in a production phase. It is important to note that the first 2 phases can be supported financially by the project itself. And in particular, in the second phase, which is the more difficult to be achieved, we can take over up to 80% of the cost and subsidize it with the money provided by the European community. Of course, if everything goes well and we are able to fulfill your specification after the production phase. We can envisage that a full-scale production phase, which is not longer within MIRFAB, but is taken over by the industrial partner of MIRFAB. Well, this slide presents the MIRFAB consortium, putting together the major players of mid-infrared chemical sensing in Europe, including component developers, suppliers, RTO, and early adopter of our technology. It is worth to note that at the end of the project, MIRFAB will still continue via the 4 industry that will continue to provide access to the pilot line facilities and services, and that will continue also to commercialize these devices for the user of the pilot line. Well, to conclude my presentation, MIRFAB is a pilot line providing service for the prototyping of miniaturized mid-infrared chemical sensor. The access to this prototyping pilot line is open and is to all companies aiming to develop novel sensor for novel application. MIRFAB is also a unique entry point for the fully supply chain in the mid-infrared chemical sensing. If you wish to have more information, please go to the MIRFAB website or write us at info@mirfab.eu. Thank you for your attention.
So here we are back to our room. So thank you very much, Sergio, for your contribution. Now, as I mentioned before, Sergio is here, so we can still have the opportunity to ask a few questions to him. So, Sergio, you belong to the, I correct myself, know all this, you cannot say all this, but to the experienced pilot line. So for me, it would be nice to know if you would like to first look a bit at the past, so that's something like a lesson learned from MIRFAB, that you say, in this case, we had to learn something and we could improve in somehow at some point, and also looking at the future, how these pilot lines will be prosecuted, because I saw you named 4 companies and 4 partners of MIRFAB, so it's a bit of the organization. My questions, how will you organize this? But please, first question, past and then future, please.
Well, concerning the past, my experience is that it was very difficult at the beginning to foresee which model we should follow in order to make this technology available for potential customer. I would say, looking to the past, it is clear that getting customers for the pilot line was kind of hard, and this is probably one of the weakest points we have to point out. However, I have to say that together with EPIC, by the way, we had the possibility to disseminate this technology, and we can see it by the progress that the 4 companies that are working with us have done in the last 4 years of the project. I can mention, for example, but it is not the only case, Vigo, who had a huge growth in terms of people employed, in terms of business generating. And this is also true for Nanoplast and Alplazer and Mirsense. So at the end of the day, we can measure the effectiveness of the pilot line, not only by the fact that we have customers directly, but also for the type of business that we can generate for our partners. That's the first point, and in my opinion, should be taken into account and evaluated. As for the future, in my personal experience, the point that we will have to work out is how to handle the transition from the end of the project up to the day +1, where we are alone, facing the fact that we have to be on the market, and we have to obey during the first phase on all the rules that are given by the European projects. That's the sort of a problem that we have been facing, and honestly, we don't really know yet how to do with that. And the other point is how to bring company together and foresee a business model that can fit for everyone, while keeping, of course, organization like mine to play still in this court and still be able to progress and develop a new technology. That's where my thought about this problem.
But that's a good point, because anyway, also from other experiences in the past, or also from other maybe partners that you have now, maybe you can collect and also keep us informed, of course, about the development, because new pilot lines for sure can learn from what you will experience in the future. So we are definitely looking forward to have your in a few months, also really after the final, really the end of the pilot line official, how it goes, and it will be really interesting, because as I said, not everybody reached this point, and then you have to see if all your expectations are correct and how to potentially change and adapt in case something goes wrong. So thank you very much. So then I have to say, you're welcome. So now we have actually an open questions from before for Rolando. So Rolando is actually still here. Maybe he can answer himself. It's also technical questions, but from Peter O'Brien, so our next speaker. Maybe Peter, if you want to ask your question yourself, otherwise I read it as you prefer.
Hey, Peter.
You are now unmuted, so we should hear you, but it's not yet the case. In the case, maybe I read the question, because you wrote it to me. So the question to Rolando is, are polymer micro-optics suitable for solder reflow assembly processes, like for example, at 260 degrees of temperature?
260 degrees. This might be a bit too high, but we should look into materials. There are some materials like sol gel materials that are a mixture of polymers and inorganic materials that could withstand these temperatures. So this can be discussed.
Yeah, hello, can you hear me now?
Ah, yeah, now Peter, perfect.
Yeah,
welcome.
no, it's interesting. Yeah, it's interesting because a lot of what we do now in manufacturing has to be compatible with solder reflow, because as the components are packaged, they might go onto a printed circuit board and they're reflowed through a furnace at typically 260 for a couple of minutes. So that'd be a very important criteria.
Mm-hmm. I don't have the answer on top of my fingers,
sure,
but I think we should look into materials and a solution could be found. So maybe not directly polymers, so not UV lacquers, but UV curable sol gel materials. I'm pretty much convinced that we can find the right one.
Okay, thank you.
You're welcome.
Very good. So it seems like we have further discussion going on. That is, of course, very good for for this event, because we always like to have exchange here. But maybe if it goes on even afterwards for who knows, some other collaboration is always a good to hear. So hopefully it works. Rolando will make it work.
Sure, we need to actually network the pilot lines, as Jose was saying at the beginning, and this is part of what we'll have to do in the next months.
Yeah, this is definitely.
Can I also ask a question to
sure.
Rolando?
Definitely.
This is Sergio. Rolando, what about mid-infrared micro-optics? Do you have any solution foreseen?
Yeah, well, our micro-optical components can be used for mid-infrared too. We had projects in the past in the mid-infrared. It's always a matter of materials. So we were making, for example, micro lenses for medium infrared photodetectors.
Sounds good, Sergio. Huh?
Yes, exact. It was very good as an answer.
Very good. Then I guess you have a tentacle already also to MIRFABs. Rolando, I guess this was a good invested time to have. So thank you very much for your contribution. But I guess the one with really the tentacles everywhere is our next speakers, because Peter O'Brien is now your time to rock. So it's a really pleasure for me, because we are also collaborating inside MEDFAB with Tyndall, so that's why it's I already know what it means to be really engaged with Tyndall and Peter. So I give a brief introduction to your talk, Peter. So it will give an overview of photonic and electronic packaging technologies and how these technologies are new being brought to commercialization through a large-scale pilot line funded by the European Commission. Called PICSAP, the pilot line provides users with a wide range of advanced photonic and electronic packaging technologies with the ability to scale manufacturing to medium volumes. PICSAP is strongly focused on offering standardized packaging technologies and is working with its global partners to establish a detailed set of packaging design rules and technology roadmap. So here is the time. I see the floor is ready, and I assume Peter as well. So please, Peter, Brian, you can have the ball and start your talk. Thank you.
Okay, can you see my screen there,
Yes,
Francesca?
it's all totally
okay.
Fine. Thank you.
Okay, thank you very much. So hello to everybody, and very nice to meet some of you again, and maybe to meet some new people. Hopefully we'll meet face to face in the not too distant future. So really what PICSAP is about, and you've probably heard a lot of this before, we've got some updates, is around three main areas. So it's providing packaging services around standardized packaging for optical, electrical, thermal, mechanical, etc. And that's continuously being expanded. We also provide training and education. So as part of our remit and as part of our sustainability, we've built up a fairly successful education and training program, and that funds what we do in our pilot line as well as training people. Another important activity is we're working on the PIC ecosystem to work around standards and roadmaps. That's done in Europe, but also we're starting to work a lot outside Europe, in the US and in Asia. So working with other packaging facilities and foundries to standardize packaging technologies. Just very briefly, we have a large number of partners. Most of them are in packaging areas, but we have other partners who are helping us validate those technologies. And more recently, we've had some new partners join who are bringing new capabilities. So Vanguard are bringing optical wire bonding, photonic wire bonding, and freeform printed micro-optics, FIX, more packaging capabilities. Fraunhofer, some interposers and SUS, micro-optics, and Octoscribe in the UK, working on optical waveguides and interposers as well. So we're continuously expanding and adding more services and technologies. I think one of the big lessons we've learned was we had to have a very clear offer. So it's quite complicated sometimes trying to explain to users, especially new users, what we do. So this view graph captures pretty much everything we offer in some shape or form. So we have photonic wire bonds, micro-optics, optical fiber packaging, laser integration, wire bonding and flip chip integration, different types of interposers, and packaging as well. So for thermal and for fluidics, biosensing, etc. And we have a whole menu of that technology. This is a nice example. So in our internal activities, where we're not working with outside users, we've got an internal program. We take those technologies and validate them between ourselves. So this is a data communications module, which is currently being tested. And you see many elements of those packaging technologies that I showed previously in the menu. So we have flip chip integration of ICs on a PIC. This PIC was made by IMEC. It's a standard MPW offer. Laser integration. So this is a hybrid laser with micro-optics coupled into grating couplers, micro lens arrays for pluggable connectors, and all the ancillary packaging things you need, interposers. And again, these are all standardized now in PICSAP, and we can offer those. This is a nice little video here showing a complete module. So there's that little module in the previous subsystem. And again, you see the interposers with the RF connectors and the DC connectors, all standardized and laid out according to design rules that we worked with, for example, with Synopsys. So that's in the PDK. I think one of the big developments from an internal perspective, which we worked on, which is becoming quite interesting from an external kind of perspective, is what we call our reference PICs. And these are basically photonic chips which contain a range of optical and electrical IOs. So optical edge couplers, grating couplers, DC, RF wire bonds, areas for flip chip. And essentially what we're using those were to validate processes. So we're not looking at actual product functional devices. These are just test structures so we can use them internally. And there's quite a bit of interest now from foundries around the world who want to use that type of layout to validate their foundry processes with respect to packaging. We're also now looking at integrating micro-optics for edge coupling, for pluggable connectors, and lasers as well. So bonding lasers directly flip chip onto these chips. We have a number of those reference designs now with foundries within our pilot line in Europe, IMEC, Lionex, Smart Photonics, the IMEC BioPICS process, and also HHI, which Kevin spoke about earlier. And we've got basically standardized optical and electrical I/Os for all of those foundries. And we call them an ADK as opposed to a PDK. ADK stands for Assembly Design Kit. And basically those configurations now are in the design software. And what we show here is we originally started, we kind of just documented them in a kind of a handout we gave to people. And in PICS app with Synopsys, we've integrated that into an ADK, and users can basically use the software and follow our design rules. So a very nice example here is with a biosensor. This is, again, internal work to show users what we can do now around standardization of packaging building blocks and packaging designs. So this is spotting of biosensor antibodies on a chip. This is a silicon nitride chip. And with Randox, who are one of our partners, and we're working on spotting of COVID-19 antibody kind of detection onto this chip. And essentially what we have here is a design rule for the diameter of the spotting based on standardized spotting equipment and the pitch that you must respect in regard to that. And also then we have micro-optics for a pluggable kind of microchip or biochip and electrical connections as well. And that's in a PDK. So that's integrated into the Synopsys software. And here you can see an actual chip just looking down from a microscope. We've come up with a process flow, again, standardized, where we can integrate microfluidics with one of our partners, the Microfluidic Chip Shop. And that basically, that's actually been tested and validated within our pilot line. So we can offer that now as a service. And just very briefly, we've even built an instrument around that. So the biochip fits in here. And you can see kind of some of the inside of that. So you can see where the biochip is plugged in. It's a very easy assembly system. Microfluidics bring in the sample. We have a pluggable connection here. So we've got a free space connection with fiber arrays onto a PIC with microlens, similar to what I showed earlier in the datacom. And these pogo pins for electrical connection as well. So the chip can be slotted in and slotted out, kind of low cost cartridge type microfluidic PIC system. So how we work is we initially engage with users on the design phase, move to a prototyping phase and a manufacturing phase. And standards are really important. So even in prototypes, we now have a standardized prototype platform. And essentially it's like a breakout board. So we can quickly take your PIC with following those design rules. We don't have to build an expensive gold box type package. We can use these off the shelf with our industrial partners who will again work to standards. And we can quickly turn these around at a relatively low cost. So you can validate your PIC, make sure everything is working, and then we can move to a more manufacturable solution. So this would be like a high-speed, quite complex package, an RF and DC with multiple channels. This is one of our standard offerings. So we can quickly move from prototyping, early stage validation of your PIC, because quite often SMEs or even larger companies come in and the first engagement is around, we want to design a PIC and build it and test it. And then we can move to scale up. So we're not jumping straight into scale up. We're using that phased approach, but again, using standardized technologies. So we've got one location in Tyndall where the users can the customers can come in. We've got a standardized menu. And typically the way it works is the gateway at Tyndall with our research activities, we can develop the prototyping and then transfer that to an industrial partner within PICS app. To achieve that, typically the way we work is we form separate NDAs and separate contracts. It's quite an efficient process now. So a user or a customer will have a separate NDA with the gateway at Tyndall to discuss the requirements. We'll identify the best partner in a consortium, and then they will sign an NDA and contract as well. Just to show you where we are, we're running just over a year now as far as commercialization. We've got 150 validated inquiries there, inquiries that know are interested in working with us. Then we move to NDAs. Really what we're trying to get to quickly is what we call a statement of work, SOW. basically that will define a project. So that's essentially like what we use for our contract. And you know, we've got a number of projects ongoing and a number of those completed. We're a truly global pilot line, so we're focused in Europe and supporting European SMEs, but also we want to grow the ecosystem globally. So here you can see a quick snapshot around the world where we're involved. And this is just a quick example of a typical project. So this is one case study. So here you can see we're typically going for a number of months to get to a point where we can start a project. Typical projects in the first phase may be 4 to 6 months, and then they will transfer across to scale up. So we have a number of those projects in that kind of phase where we've gone from prototyping and moving into scale up. And we're in a very good place at the moment. We're in our 3rd year. We're sustainable. We're earning quite a bit of revenue. And we can see that the gateway, with our collaboration with our industrial partners, will go on well into the future. We also have a training program which is working very well. It's hands-on, and we're oversubscribed for that. So we've obviously a limited number of places, and it's something we want to grow and add to more times over the year. But that's something we're working on, and we will continue to offer that, hopefully with increased numbers. So that's a pretty quick snapshot. Really where we're working towards is building a sustainable pilot line and an ecosystem to work with our partners from design, foundries, test, and application areas as well. Thanks, Francesca.
Thank you very much, Peter. It's definitely a super important contribution yours, because we are in a phase where you are definitely in advanced one, so an experienced speaker, an experience also in pilot lines, but also I find PICs special because dealing with packaging means you can really deal with all these pilot lines almost as customers. So anyway, you can already engage in these collaborations that we also was already mentioned by Jose and also Rolando before, that if we want to learn how to interact and also collaborate among pilot lines, I guess PICs is a really good example. So can you maybe explain a bit more how is the advantage of dealing with all these pilot lines, not only single customers, but also your interactions with the other pilot lines?
Yeah, I think that's the big challenge we face now, and the big opportunity. So how we can start to coordinate things. So quite often users coming in have to go to a foundry, have to go to a packaging and find them and understand. Whereas if we can offer that as a unique one offering in some cases, that would be really beneficial. The other thing I will say is, what I don't mention here is, regional support, and I think the European Commission want that. Getting regional investments. We've got a 6 million investment from our Irish government to continue sustainability of our pilot line. So with that, AngelTech have joined us in Cork, and I think bringing the equipment in, starting to work with the foundries closer is vital, because users find it very difficult to try and build the ecosystem themselves. So we have to do that with them. So collaboration between these different pilot lines here today is very, very important.
Yeah, and also the topic, as I said before, of course, freeform micro-optics of Fabulous are a really hot topic, and many pilot lines here have their own strength in some topic. But for packaging, I can say we had this epic online technology meeting that was really having 200 people online on YouTube watching it. So there is definitely a high interest in this. And so also the thing that is for PICs interesting is also this educational part. So you're really dedicating already now a lot of time to teach basically your knowledge to other customers and also potentially to the pilot lines. Can you comment a bit on this, on how is it organized, if you have already a bit of comments on how it went so far and how is it planned to go on?
Yeah, I think what we're trying to do here is we're giving a practical course, and we try and make it relevant. So in some cases we've made tailored courses where particular companies have come back and said the generic training is good, but we also want specialized training. So I see opportunities to slice it in many ways. You can do a generic training, and you can also offer specialized training. And I will say companies will pay for it. And it's like one of our objectives is to be sustainable. So we need to be economically sustainable. And that's a really good way of contributing to that. The other part of sustainability is technology sustainable. So we've got some very exciting new wafer level processes we're starting to bring in and we would add those to our training programs into the future. So training should not be overlooked. It's a huge issue for industry, trying to get people with experience, and I think the pilot lines can really add to that. So I'd say to all the other pilot lines, both from a financial and from a networking perspective, many of the big projects we get are people who've attended the training programs.
Very good. So all who are here can still hear. This was a good suggestion. Let's learn from the lesson of Peter. I know that he's very always demanded when he's in some meetings. Well, now I guess also Peter is not traveling much like any of us, but it's definitely really nice to have you here. And there is always a possibility to ask now or also offline, I hope, to Peter some suggestions, because we know in EPIC you're always a good person for giving advice. So that's definitely already one that he was given today. And so now I guess if there is no other comment from others, we can go on with the agenda. So now it's time for another success story that we have to hear about. So PICs for Life, so another pilot line. Thank you, Romano, for being here. So I will give now a little introduction to PICs for Life. So this is a European photonics pilot line which offers easy access to silicon nitride photonics for the life sciences application. The PICs for Life consortium consists of 14 partners providing both a technology platform and supporting services such as consultancy, design support and services, chip manufacturing, and chip testing, characterization, and assembly. Innovative life sciences companies can build silicon nitride photonics integrated circuits using PICs for Life's library of photonics, building blocks, and interfaces. So Romano is here, and I guess he also wants to go live. Am I correct?
No, I spent like 4 hours to record
Okay,
10 minutes. So I'd rather go for the recorded one.
Yeah, actually, you're right. You also told me in advance, so that's a good point. So yeah. Now, Romano, we send your presentation. So now it's time for Romano to roll.
Welcome, everyone. My name is Romano Hofman, and I'm Program Director at IMEC in Leuven. In today's talk, I will present the EU pilot line, PICs for Life. PICs for Life is a European funded project which started on January 1st, 2016 and is expected to be finalized in the next months to come. The project consortium consists out of 14 different partners from industry and the academic world, and the project coordinator is IMEC. PICs for Life, as the full name is spelled out here, is one of the EU pilot lines centering around silicon nitride photonic integrated circuits. Since silicon nitride is transparent through most of the visible range, it can be used for life science applications where visible light is essential. So life science and healthcare applications need wavelengths in the visible range. Data and telecom actually need near-infrared wavelengths, typically between 1 and 2 micron, and chemical sensing applications make use of mid-infrared wavelengths, and this is the focus, by the way, of another pilot line, namely MIRFAB. Traditionally, silicon photonics is only able to serve the infrared applications, and therefore we focus in this project on silicon nitride, since the perfect base material to reach into the visible light and serve therefore a multitude of visible light photonics applications. Integrated photonics makes use of semiconductor manufacturing techniques, and semiconductors have been going through a trend called microfabrication and the associated downscaling of electronic circuits. This has fueled the transition of large complex circuit boards into small integrated circuits with billions of transistors, which also has led into a cost reduction and performance improvement. We see now the same trend happening for optical circuits, which are being replaced by waveguide structures which are embedded in photonic integrated circuits, shortly PICs. In this slide, you see a typical cross-section of a photonic integrated circuit. Most of those chips make use of silicon as a substrate, and while for silicon photonics the waveguide material is silicon, the waveguide material for silicon nitride photonics, as you can see here, is silicon nitride. which is sandwiched in between two silicon dioxide layers. So the waveguides are depicted in pink. You can also see that the waveguide structures are not all the same. So by etching the waveguides at different depths, you can create different waveguide structures. So at the extreme left, you see, for instance, a ribbed waveguide, and next to that, a grating. Then quite often, we can also open the top silicon dioxide layer to make a window. This window can be used for sensing applications and or also for microfluidic applications. Within Pix4Life, we focused on two different platforms. The first platform is the BioPix platform from IMEC, and the other one is the Triplex platform from Lyonix in the Netherlands. Those two different platforms have different characteristics, different deposition techniques, wafer sizes, etc. All in all, I would say these platforms are quite complementary and can provide a great variety of devices which have now been made available through customers of the Pix4Life pilot line. At the start of Pix4Life, we defined different objectives. The first objective was to mature the technology by performing multiple fabrication runs and developing a design library. The second objective was to improve the accessibility of the technologies. The third objective was to demonstrate the technologies, and this we did by predefining application cases which have been served by the technologies available. And the final and fourth objective is to implement an open access model through which small and medium enterprises and universities can get easily access to the provided services of the pilot line. So the first objective is to mature the technology. Many different fabrication runs have been performed in order to do so on both platforms, the BioPix and the Triplex. Over the course of the project, 10 multi-project wafer runs or MPW runs have been conducted, which were accessible for both internal and external clients. And next to that, we also conducted many different and numerous development runs to improve the technology. Next to maturing the technology, we also needed to increase the availability and maturity of the different photonic building blocks. In order to do so, we have created a multitude of different building blocks, ranging from grating couplers, filters, arrayed waveguide gratings, and multimodal interferometers. About 160 components have been designed and simulated, and 70 of those have been really brought to the maturity level that are now available for external customers. It's essential for the accessibility, and this is the second objective, that the technology is offered in industry standard design automation tools. More in particular, we needed to develop PDKs or process design kits for the different design software tools. So two different partners, Lucida and Synopsys, did this respectively for their EPKIS and OptoDesigner software tools. PDKs facilitate the process of designing and also allow to access design component libraries. And in this way, it makes the design process much easier and faster. To improve the accessibility, we also set up a connected supply chain, as you can see here. The supply chain starts with system specifications, which are essential for the photonics designer. And once the designs have been finished, they are aggregated and fabricated. This connected supply chain allows us not only to develop and mature the different building blocks, but it also fueled the 4 demonstrators which we predefined at the start of the Pix4Life project. So these demonstrators are shown here in the third objective. So at the start of the project, we had 4 different technology demonstrators. MatLumix focused on an optical coherence tomography, or shortly OCT, while BOSS has been working on a multi-sensor concept, allowing the measurement of multi-body parameters. Miltenny, on the other hand, has been developing a flow cytometer. And finally, Toptica developed a multispectral light source. These technology demonstrators not only helped in setting the system specifications for the supply chain, but they also helped in improving the whole set of building block libraries developed for both platforms. And then the final objective is to implement an open access model. This is very important to increase the accessibility of the supply chain and the pilot line as a whole. You can see here that we use the connected supply chain, and the partners of the project are responsible for different parts of the value chain. So VLC, for instance, is responsible for assisting the customer with the system specifications and the design, while Lucida and Synopsys provide, of course, the design tools. The design, aggregation, and fabrication is done by IMEC and Lyonix for their respective platforms, while packaging has been done or will be done, if needed, for the customer by Tyndall through the PIC app pilot line. Chalmers and Toptica can provide additional external components if requested by the customers. So PICs for Life as an EU project will end in the coming months, so probably in the summer of this year, but the pilot line will continue to operate. The different services provided by the different members of PICs for Life will still be available through a gateway that will be managed by VLC Photonics. The schedule of upcoming MPWs and other services is available on the PICs for Life website. MPW fabrication services will also be offered through Europractice, which has many years of experience of organizing and offering MPW runs. In addition, with every MPW run, we can fabricate also new building blocks and mature them further. And this is important to mature the PDK to a level that is really industry standard. PICs for Life will also continue with dissemination activities, such as collaborating with other photonics consortia, such as EPICSFAB and EPICS. And PICs for Life will take part in organizing events such as webinars and hands-on training. All these activities really ensure that PICs for Life can go on as a pilot line and offer its services to all customers all over the world. So this ends actually my presentation. And of course, thanks for following this talk, and we welcome you as a customer as well to serve you. So for more information, you can visit the PICs for Life website, and feel free also to email us if you have any questions. Thanks for following this presentation, and stay safe. Bye.
Thank you very much, Romano, for your contribution. So now we have you here also live. So. Yep. Happily willing to answer questions and discussion here. Just as a reminder, we discuss happily here, of course, is a nice room to chat, but also we welcome questions from attendees outside the Zoom room that want to ask a question in the chat. But at the moment, I would like to say to Romano, so thanks a lot again for the contribution. And I saw a bit, as we heard also before from other pilot lines, I would like to talk about the structure that PICs for Life has. So as you mentioned, one of the two platforms, so we have two platforms delivering the service. That is, one is, let's say, at home, so IMEC, where we are also working, and the other one is Lyonix. And so basically, it's a way of diversify the offer, right? Correct. And I would like you to comment on this, and also on the diversification you have at the end, so that you plan now at the end of the project to have Europractice and VLC that will interact with the future customers and bring over also the results. Can you a bit comment on this? What the others can learn from this?
Yeah, that are a lot of questions into one sentence, I would say. So to start maybe with the two different foundries. So we have indeed IMEC and Lyonix. I would say also, as I said in my talk, they are quite complementary. And of course, the customer is king. Yeah? So the customer decides which foundry and which service he needs. So if a customer comes in through VLC, that's a neutral source, then of course VLC will do for the customer and select the platform that is best for the customer needs. As you remember from my talk, VLC will guide the customer through his system specifications, and then if needed also support him with his design. Then the question about Europractice and VLC. So also those two are quite complementary. So typically a customer who knows how to do IC design, or in this case PIC design, they will come to Europractice because they don't need support from a design house or a gateway. Yeah, so they come to Europractice, and in Europractice we have a neat separation, so that the IMEC, so the BioPix platform, will be offered through IMEC as a service center. But the Lyonics one, on the other hand, will be done by our partner in Europractice Tyndall. There was actually a press release yesterday, so it's quite good that this was done just before this meeting. And then secondly, when a customer doesn't know how to do PICs, then it's better that he follows the gateway. Yeah. So I hope that answers a bit your questions.
Yeah, definitely. It's really like the structure, because as we saw, not everybody, not all the pilot lines are organized the same. And so it's a really also lesson to learn how other so success story are working, especially in your case that you are already mature pilot line. And so now the other question is a bit, you can choose. You either choose what you learned from the PICs for Life experience that you would like to say share with the other pilot lines, or maybe a challenge that you think that we know, of course, at the end of the pilot lines, we know the usual challenge, but maybe you have something that you would like to face and tell us, and if maybe someone can help you with this, or if you have already a straight plan for the future.
Yeah, so the biggest challenge we encountered was actually to find enough meat on the bone for all people in the value chain. So for, like I said, for the MPW services or the foundries, it's quite obvious and not so difficult to find customers. Although, I mean, it's not trivial. I mean, I don't want to say that. But for instance, VLC, and also to a less respect for Synopsys and Lucida, it is more difficult to find new customers because, for instance, to look to the software provider vendors, they have already a quite large portfolio of customers, and so it's difficult to get to new customers. And then secondly, VLC, also there, I would say it's not so trivial to find those customers who don't know PICs yet and would need their support. So that is maybe the biggest thing we were struggling with, but I think we have now found a method to deal with that.
Oh, that's good. So that means that that helps also, and so that means that not always. So diversification is really important, and it should be maybe pushed more in order to engage also all the partners and to also detect where the lack of information or needs in the potential customers are. So that is a good lesson that the new pilot line should learn. And thank you for sharing this. So now I guess if I don't see other comments, if someone else wants to comment, we can proceed with our agenda, because now it's time for Gloria to take the floor. Thank you very much, Romano, for your contribution. And now, so we have Gloria Höfler, that is Director of the Advanced Development at Infinera. So Infinera, just a few words about it, is in partnership with the AIM Photonics developed a turnkey indium phosphide photonic integrated circuit foundry capability that addresses key scale-up challenges to transition from prototypes to high-volume manufacturing. The turnkey foundry capability was developed leveraging best practices embodied in the design and fabrication of commercially deployed monolithic integrated coherent optical communication system on chip, so SoC. Various commercial electronic and photonic design automation platforms were customized to provide the scalability necessary to bring an indium phosphide-based foundry process into manufacturing. Example of the electronic photonic design automation tools corroborated with experimental PIC results will be discussed. So now Gloria is here, but we go first we let the virtual past floor. So
by the way, thank you, Francesca.
Yeah, you're welcome. So now it's time for the offline Gloria. So see you in a bit later, and let's listen to your contribution. Thank you.
I would like to thank the workshop organizers for the invitation to present on behalf of the Optical Innovation Center team on the ongoing efforts to scale up the indium phosphide foundry at Infinera. For those of you who are not familiar with Infinera, company was founded in 2001 to commercialize optical network systems with differentiated PIC platforms. Our systems provide solutions across the entire optical network infrastructure, with customers encompassing service providers, data center operators, all the way to the enterprise and verticals. We are a vertically integrated company. We design and manufacture our own PICs, our drivers, the modules, and all the way to the line card and the firmware that is used in the optical network system. The Optical Innovation Center houses under one roof all the key technologies required to deploy high-performance optical engines and take advantage of the performance synergies between these technologies. It is with this system-centric approach that we design a state-of-the-art PIC foundry capability that offers users a complete go-to-market solution, inclusive of customized ASICs, TIAs, and RF optical packaging. I will focus primarily on the indium phosphide foundry because one of the challenges faced by photonic foundries today is a reliable path to pilot and manufacturing volumes. Infinera, working with AIM Photonics, developed a PIC foundry capability that provides users with optimized building blocks that can be readily used to prototype PIC-based solutions in their applications, starting from concept to prototype all the way to production. This is accomplished by three key features. First, by using a commercial fab line that has a proven track record for deploying state-of-the-art PICs in an optical network. Second, by incorporating best practices inclusive of an EPDA environment. And third, by focusing on the user's cycles and reducing their learning cycle to achieve a commercial path. No prior PIC layout experience is necessary. And the customer and the user really can focus on making that PIC solution work in their specific application. Now, how is the ramp up and the pilot line challenges? How are those addressed? First, the integration platforms and the PDKs, all the components are developed with the manufacturing capability in mind, similar to what processes that are used in the electronic IC industry. It is important to understand the line capability and how the tools and that capability translate to device and platform performance. Fab processes are developed with very tight CPKs. Then end-of-line tests are used to correlate the performance and develop a set of design rules, both for the capability and for the device. SPC metrics are used to confirm and modify DRC and then deliver a high fabrication yield. This iterative process results in an integrated device performance that is compatible with state-of-the-art and standalone performances today. This already has been demonstrated in Infinera multiple times, and I'm showing it here by the performance of the commercial monolithically integrated 1.2 terabit coherent transceiver PIC. You can see from the cumulative distribution that the performance on the C and L band are very similar and are all within very good tight distributions. These learnings from one generation in one integration platform can be readily transferred to another product line. So that's shown from the C and the L band performance. Next, I'd like to show how the development of the processing technologies has significantly improved the manufacturing capability of 3.5 photonic ICs, even in comparison to silicon. The wafer fab yields for various PIC product lines are plotted versus time and normalized to 10 masking levels. Each product line has reached over 90% wafer fab yield, in spite of the increased complexity in functional integration, as can be seen from the OOK wafers to the coherent transceiver product line. A reduction in the random killer defect density is also very important, as more functions or channels are integrated monolithically into a single chip. This graph shows the reduction of the killer random defect density as a function of time with each product line. Furthermore, the coherent transceiver products show how each integration platform builds and benefits from the previous generation, as can be seen here. Another important feature of the pilot scale-up is the EPDA environment that is needed for scalability and sustainability. Today, Infinera has released 2 PDKs, each platform consisting of capability that enables the monolithic integration of all the requisite optical functions needed to fabricate a TX and an RX PIC. Each building block consists of a single or a composite P-cell and has been fully optimized, or it's really a turnkey component. And the EPDA environment is used to achieve consistency, provide hierarchy, and scalability. Fully optimized IQ modulators, MZI-based filters, balance, and other types of functions are offered for the user. Once the PICs are fabricated and completed, they are delivered fully wire bound on a ceramic carrier that is compatible with automated testing and further sub-assembly. A key feature of this foundry, which supports a smooth transition to high volume, is that all the PICs are fabricated in Infinera's manufacturing line, using best practices for reliability and with a well-established manufacturing baseline. Compact models are generated based on actual device data and statistical variation. The kit is available through various commercial users. This capability allows users to design their PIC schematics, building them from symbol libraries, and then take that schematic and simulate the circuit. Once the intended outcome is achieved, the schematic is automatically converted into a netlist that can be imported into the layout tool for further layout analysis and design rule verification. The netlist export capability is really important because it allows us to reliably lay out the intended circuit schematic. PIC simulations are tested with various control vehicles to verify that the experimental and the simulated results are within some reasonable expectations. Now let me show you some examples of these demonstrators. Here I'm showing a TX and an RX PIC monolithically integrated to realize a PAM4 circuit transceiver. The PIC symbols from the PDK are used to build the schematic. A pseudo-random binary sequence provides the electrical stimulus to drive the MZM and generate 4-level voltages for the PAM4 format. The PICs can be probed at various points shown here in yellow. The simulated electrical eye diagram corresponding to scope 2 is shown on the top figure, as well as the receive optical eye diagram. And then we can compare this with the experimental results obtained from the actual PIC that was simulated. The next vehicle used provides an insight into the complexity of the PICs that can be designed with both the tools and the PDK capability. Here we demonstrate the implementation of an advanced modulation format transmitter and receiver PIC vehicle. A 16-QAM optical coherent transceiver is built using the Infinera PDK models, and a nested IQ modulator is used to implement the TX side. On the receiver side, we have an integrated LO, 90-degree hybrids, and 4 PDs. Using VPI photonics, clock recovery, DAC, and DSP functions, a constellation is simulated, and you can see at the bottom the good correlation to experimental correlation. Lastly, advanced PIC designs need bidirectional interoperability between simulation and layout tools. We've shown that one can start from an abstracted architecture and simulate it and bring the netlist into the layout tools. This is called schematic-driven layout, and it's the golden standard for ICs and silicon. However, layout-driven PIC design is more commonly used in photonics. So to verify that the PIC layout meets the intended design, its netlist is generated and exported from the layout tool. The netlist is then automatically converted into a PIC schematic that can be readily simulated. Design hierarchy is supported, and auto placement of the components is also possible to keep the correspondence between the circuit and the layout schematic. This EPA features support users with simulations to reduce prototype cycles and sustain multiple production processes. So in conclusion, I have shown how at Infinera we've developed a pilot line that prototypes and has the capability to go into full volume manufacturing and supports PIC from concept all the way to customization of the product line, including the capability to design TS, ASICs, and packages. We have a turnkey PDK that reduces prototype cycles. It is competitive with state-of-the-art components and sub-assemblies. This capability was designed in collaboration with AIM Photonics and provides a smooth transition to manufacturing through the use of a commercial line, interoperability of EPDA tools, and reduced cycle times to users. Thank you for your time.
Thank you very much, Gloria, for your contribution. And it's really nice from you to be here today for answering a bit of questions and commenting on your fantastic foundry you have there. So I did say the difference that one can see immediately towards, so in comparison to our pilot lines. Are you there, Gloria? Yes.
Yes, I'm here. Yes, I'm here. I can't switch my picture, so.
No problem. Important is that you're there. I can hear you. No, I was just asking. Of course, your example in comparison to the pilot lines that we have heard so far is that, of course, it's this verticality. So basically, you're structured. So the organization of you together with AIM Photonics dealing with this foundry. And it would be nice for us to know a bit in comparison to a more horizontal structure that are usually the European funded initiatives. What are a bit an example of advantage and one disadvantage for that, of being vertical?
Okay, well, thank you for the question. I'm not sure that I can really answer, the advantages or disadvantages of the horizontal, but I can tell you a little bit more about the advantages that we've seen in being vertically integrated. Especially, we have really benefited from our colleagues in Europe in particular, because they started the foundry services much earlier than we did in the United States, to be fair. And so there's a lot of education that has gone on with the users. And that has really helped so that when users come to a foundry, they have some idea of what their expectations are. But I think, the advantage of being vertically integrated is that we can then work with users and understand what the system requirements are. And so starting from the system requirements, we can drill down to what they will need in terms of controls, drivers, and electronics, and then in some of those things in the package. And I think, that's really the advantage of being vertically integrated. I think when you look at a horizontal, when you have to go to different sources to do that, you have to just really be mindful that at the end of the day, what you're trying to solve is a problem, a system level problem. Because if we don't solve a system level problem and we don't put, this PICs into specific applications, our industry is not really, going to grow. So, making sure that you're mating the metrics of the system back, as you go through various, houses or the foundries, the packaging and the electronics and all that is, I think that's the challenge when you're horizontal. So you need to have that thoughtfulness right from the beginning and that expertise. Whereas if you're vertically integrated, that expertise is innate into your design. I think that's what I've observed.
Yeah, definitely. I understand your point, and of course, being in a community, so being in initiative that is funded by the European Commission, of course, horizontality is also an unwritten challenge, let's say. So, as you say, you are a bit more lucky in this way but from what we heard so far, I guess we had already many cautious coordinators or partners that already mentioned we think about this already in advance. So I guess they also learned from maybe vertical experience. So it was nice to hear that you learned from the European experience also to work in US in this way. And so I guess they can also learn already from other experiences and say, okay, this will be one challenge for sure. So let's be mindful and think about it in time. So that's also a good suggestion from your side. So I see we have a question. Now, that's it. Yeah, from François Menard. Thank you again for one question. The question is the Infinera Foundry service available directly, not through AIM? That was meant like this.
Yes, actually, AIM set us up so that we can, there's a lot of infrastructure that goes with having a foundry, especially if you're using a commercial line. You have to keep the processes fresh, and you have to make sure that the platform is differentiated from your other product lines. And so, so AIM and Infinera, partnered to do this. But now we're coming to the 5-year end of the AIM program, and Infinera will carry on with this capability. And so we do offer the foundry services through Infinera directly.
Okay, so that means that also this would be also my next question. So looking at the future, you are now basically fully independent, and you will try to keep on and getting customers on autonomously, let's say.
That's correct. That's correct. Yes.
Okay. Okay. Do you see
and
challenges
we look forward
there?
To that. Yes,
okay, you look forward to that. That's good.
There are challenges always finding customers who are also interested in scaling up. And so that's always a challenging proposition for any foundry.
Okay, but the mood seems very positive, so I don't feel that you're scared from this. So that's good luck, of course, and hopefully we can hear also in other events. Maybe you can also talk about in one of our EPIC online technology meetings, maybe in future, or also in person, about the experience that we have with this solo activity. Then, so we look forward for future updates.
Yeah, I look forward to that. Thank you.
Thank you. Thank you so much, Gloria. So I guess, as usual, I'm keeping the schedule not really well. They will always say the Italian speaker, the Italian moderator talks too much. But so let's maybe then move forward. Now it's time for AngelTech. So Michael Geiselman is here. So thank you very much, Michael, for being here. So I will just introduce briefly your contribution. So possibility of thick film silicon nitride is your talk. So Michael is managing director and co-founder of AngelTech, and basically silicon nitride photonic integrated circuits offer new possibility for existing and emerging applications. This we heard already. Applications such LiDAR, communication, quantum, microwave photonics, and biosensing benefit from a transparency window from the visible to the mid-infrared. The ultra low losses in those wavelength ranges, and good power handling of CW and pulse laser. AngelTech's the all nitride core technology results in a high mode confinement, low loss, and small bending radii. Examples of PIC applications and integration with other platforms will be presented and their challenges discussed. So, Michael, we are really looking forward to your talk.
Thank you.
Is it all ready? Yes, it's coming. Now you go in presentation mode, and we can roll. Yes, the floor is yours. Thank you.
Thank you, Francesca. Thank you for the introduction. I will present here AngelTech, and whereas we are not a direct user or participant of one of the pilot lines, we are very much in contact with many of the different members of the pilot lines to complete the full PIC value chain. And I would like to start, that was probably already addressed, and I thank Romano that he gave a good introduction into silicon nitride, so that I don't have to give this anymore. But we actually have already silicon photonics, and in certain applications, data centers, telecom, and a few medical companies. But the application space is still large, and there's many other things that can be studied, like LiDAR space or aeronautics. However, in silicon photonics, you have usually high propagation losses, low optical power handling, so you get to photon absorption, narrow transparency windows if you go to the visible, like Romano already mentioned, and the fiber coupling, especially edge coupling, is quite cumbersome in silicon photonics. And with that, we want to solve most of these issues by having a silicon nitride and not the silicon nitride with the thin film, but the silicon nitride with the thick film, having like 800 nanometers of nitride, where the mode is entirely confined in that waveguide, and that gives us a few key advantages, which is very low loss, because we use nitride and the mode almost doesn't see the surface roughness. We get very small chip sizes with very small bend radius, a very high yield, and the transparency range of silicon nitride and high optical power handling. So no true photon absorption. So we have in that we have two things. We have low loss and very small chip size that combines a bit the two worlds of silicon nitride and silicon photonics. And this slide is about the ecosystem of a PIC manufacturing process. So you go from design to chip manufacturing, packaging, module and system integration. And our core expertise is the chip manufacturing, where we offer R&D support, and we offer good known dies from prototype to volume. And for example, a customer can come and send us a design or what he wants to do, and then the circuit design stays with the customer, and we deliver chips. And where the other partners of the ecosystem come in is that we work with design houses and software providers to have the PDK, our PDK, available to the customers, and with packaging partners to get not only a chip but also a packaged chip delivered to the customer. Our similar to the other presentations, that we also offer custom runs and multi-project wafer runs. Custom runs can start anytime. There is a fast-tracked option below 2 months delivery. We have a full choice of process modules in a custom run, and you can even change a few things about custom thicknesses and quantities of chips. In a multi-project wafer run, we offer 2 silicon nitride thicknesses, one at 800 nanometers and one at 150 nanometers for the visible wavelength range, and 800 for the IR wavelength range. And you get in 10 weeks time, you get 7 chips. You can also have more chips if needed, and tape out dates are 4 times per year. We also have additional modules that makes this platform compatible also with other integration. We have you can have a 2-level waveguide, so you can put the mode from one layer to the other. So you can even put more dense structures on the chip, for example. We have heaters and local cladding opening to access the evanescent field of the silicon nitride for sensing or for bonding applications if you integrate lasers or other components, which I will mention afterwards. Our design kit offering, similar to what was mentioned in the previous talks, we have components that were designed, fabricated, and measured, and this is an iterative process. where we then have very good performances after a few iterations of certain passive building clocks. We offer spot size converters to couple an SMF28 fiber, for example, and heater modules to tune phases of ring resonators or Mach-10 interferometers. And just as from an example that was published here in that paper, that's an example of an atomic clock. I want to walk you through where we can be of benefit with a thick film silicon nitride and our process modules. First, that's one of our key components, a high Q resonator, where you can put a CW light in, and because of the very high Q and the Chi3 nonlinearity of the resonator, you can generate the so-called frequency comb, where the new laser lines are generated with a separation defined by the radius of that ring. We can also with our platform engineer different modes for coupling, especially for coupling a laser chip, butt coupling, or also coupling, as mentioned, single mode fibers to the chip with very good efficiencies. And here in this picture here, it says frequency doubling. So what they need is they have a signal in the infrared and need to double that signal down to the visible 770 nanometers, and this is done with frequency doubling. And what we have developed in our platform here is a process where we open a bonding window where 3.5 or lithium niobate chip can be bonded through molecular bonding, and through the evanescent field, the light can be doubled in that lithium niobate chip. And with the same module is used to do, for example, photo detectors. And that work was together with Andreas Behling at the University of Virginia, where he showed after the bonding and after the integration of a 3.5 die on our interposer chip, a photodetector that went up to above 10 gigahertz with a very good responsivity. And that shows a bit what you can do with photonic integration. So from a system, what I showed here that looked like 20 years, a bit like that, is nowadays available as a rack system. But the idea is really to get this down to a chip level. With this, I would like to conclude. In AngelTech, we offer the basics of silicon nitride with a high mode confinement, low loss, small footprint, and high power handling. We have a platform that makes it easy to integrate other active components such as 3.5 materials or lithium niobate. We have developed a PDK that people can use for 1550 and for the visible wavelength range. And we know that world connections and packaging are important and have modules there to ease that and to get the best performances. And that you can try out in MPWs or in dedicated runs with a very fast turnaround. Thank you very much.
Thank you very much, Michael, for your contribution. It's it's really impressive what you can do on the Stru. This last image of the time scale, how they were in the 90s, the lasers, they were also already in the 2000s still so cumbersome. So it's really nice to see how you can really now reduce the size, and with the PIC technology, you can really do something that it was unimaginable a few years ago, and now this is possible. So looking at your organization, so as you said at the beginning already, you're not in a pilot line, so you're not presenting a pilot line because AngelTech has its own way to proceed, that in comparison to Infinera, I would say is a bit more horizontal. So as you say, you have a core experience in the preparation, but then you have a lot of partners, of course, that that are supporting you, and also reaching the diversity of the offer that you want to give to potential customers. So would you like to comment a bit on being you a co-founder, how you develop this partnership with this partner that in other cases are just through an application to the European Commission, but in your case is really probably based on years of collaborations and interactions?
Yes, so we started with more or less a fabrication process, and that fabrication process was demanded, and so we said, why don't we offer that also to other people? And then it was really going into the ecosystem, and there we run in open arms, more or less. That people were very collaborative in terms of setting up a PDK together with VLC Photonics, Lucida, and Synopsys, and really everybody knew this was already 5 years ago, so everybody knew this will grow bigger. So it makes sense to work together as an ecosystem. To provide design services, PDK offerings, and afterwards packaging, which we have heard from Peter is still key in really getting the device out to the customer.
So then the question is now, we know you very well, so in EPIC you are very active, and we know you know very well the pilot lines that we presented here and also outside of this platform. So what is it exactly that you, let's say, learn from them, from this initiative, or what can you teach them? So because we are here a bit to exchange among different experiences. What would you say it's your learning point to sell, let's say?
So in a way, like every pilot line, we can also consider us a pilot line by our own, but that's you need to work together with the whole ecosystem. If you're not in Infinera, and then you have limited expertise and you're very good in one thing, but probably other things, there is other partners that can do that very well. So it is very good that there were Lucida and Synopsys as software providers who implemented a PDK. There's no sense to now to write a new software to do that. And the same goes for packaging. There are so many people who solve problems of packaging, and here I'm very much in favor of standardization. What Peter mentioned, to get a standard PIC out that everybody can doesn't have to develop the package from scratch.
And then I would like to add, you also, not being a pilot line officially, you don't have an official dissemination manager like EPIC, but nevertheless, being an EPIC member helps you to have a lot of dissemination opportunities. I guess you can recognize this, right?
Yes, of course.
Very good. So we basically completed the pilot line also in this new way. So thank you very much, Michael. I guess yeah. Thank you also for maybe staying here a bit longer. And now we go on with our agenda. So now it's time for Hewlett Packard Enterprises. So we have Thomas here, that is photonics research engineer at Hewlett-Packard Enterprise. So he will talk a bit about how bridging R and the fast D in R&D module. So just talking a bit about the presentation, photonics teams in Hewlett-Packard Labs have been partnering with multiple leading players for pilot line service in design, fabrication, and packaging. It allows innovative proof of concept validation and sets a solid foundation for mass production development. In this talk, several good examples by leveraging this model will be discussed. So we really look forward to Thomas' talk. So now we proceed. It's a recorded one, so I need a bit of time. I'm a bit slow, but hopefully we get there. And now it's time for Thomas.
Hello, everyone. I'll talk today about how Hewlett-Packard Enterprise is bringing its devices from a research phase to commercialization, and how we actually heavily rely on pilot lines to do so. So what are we actually looking into in Hewlett-Packard Labs in HPE? We're designing this thing which is shown at the middle, at the right of the middle at the right of the slide, which is basically a DWDM link based on microrings. And this is kind of the replacement of other technology that we develop in labs, which is based on VCSELs, which is for coarse wavelength demultiplexing instead. And so for the silicon photonics microring based link, we do research on almost every aspect of that optical interconnect, and that's something that you see from the device perspective at the top of the slide, where I listed a couple of devices that we're looking into. But we do not only do that, we also look into the use cases of those optical links, and will then investigate, for instance, which type of topologies, network topologies that could be used in high performance computing use cases, such as exascale computing, or other relevant use cases. Okay, so this is what we technologically are doing. What are the metrics or the ambitions or the goals that we put out there for ourselves? You see some numbers on the left of the slide. I don't think there are a lot of surprises there. The numbers that you see are mainly a summary of what we think would cover most of the use cases that are there in HPE. So that's, for instance, getting a link which takes less than 5 picojoules per bit for a bit error rate of less than 10 to the minus 12. You see the cost numbers. You also see a certain range, which is in correspondence with what you would need for HPC or data centers, and so on. Okay, so that's what the numbers that we are after. And then how would we do this? Well, in our view on how we should commercialize silicon photonics, we don't believe that we have to work in a vertical way where we, HPE, try to do everything. No, we really believe that there's already a community out there with a lot of different players, and we think that the only way to make silicon photonics cost efficient is by leveraging that community that is out there and work together with all those partners to offer things to products to our customers. And so key there for this presentation, obviously, are the foundries. Eventually, we would obviously only work with volume foundries to ship our products. But those volume foundries would use our silicon photonics PDK that we're currently developing, and it's for the development of that PDK that we actually really rely on pilot line foundries. Okay, so how do we build our PDK? It's kind of shown schematically on this picture. I don't think there's a lot of surprises there, but there's a loop between doing fabrication, measurements, and then updating the rules that are out there that people can use to design their components. There are some things missing in this slide, such as the work that we do to model those devices, but let's first focus on the first step. So doing a tape out to make a design of experiment of a certain device so that we can understand it better and use that information in our models and also in design guidelines for our future users. You see an overview here. I think the keyword here is that in everything that we do that is related to design, we really believe that automation is essential. And so here we show an example of how we would make a test device for microrings. And then a typical die would maybe contain on the order of 2,000 microrings. So making the circuit of the microring test structure itself, there you could use a variety of different layout tools. We think that it's important that those layout tools enable us to work with open access, because that also will be useful for our eventual users, that they use this open standards platform. And then to do the assembly of the design of experiment, in this case, I'm showing how you could do this with a tool offered by Mentor Graphics, but as we've seen earlier during this workshop, there are also other tools who enable you to do this type of big design of experiments. Again, key from our perspective is that we really like scripting in our layout, and we prefer to script in Python. So tools that allow us to script in Python are the first ones that we will work with. And in our opinion, it's critical that pilot line foundries also allow us, obviously, to work with our preferred design tools. Okay, so once we made our design of experiment of, say, 2,000 microrings, we have to measure it. For that, we use wafer scale measurements. And there's also a lot of things not shown on this slide, but obviously we need a lot of design measurement automation to be able to do this efficiently. Once that's in place, and that's something that we actually do in our own labs, we get some nice figures, like you see at the bottom left of the slide. Those nice figures would then allow us to judge based on the measurement results, which geometry parameters are nice, which are giving us the optimal device performance. And that knowledge we would both feed back into our design rules, but we would also feed it back into the simulation models that our users eventually would be able to use when they do circuits level simulations of the things that they would design based on our PDK. So where exactly then do the pilot lines fit in? If you go back to the slide that I showed initially, I now color-coded at the top which types of devices are still more in the pilot line phase, or which are not mature enough yet for us to test in volume fabs. There are a couple that we are already testing now in volume fabs, such as grating coppers, traditional PDs, microrings, things like that. But in the next couple of slides, I'll briefly dive into the details of some example devices that are still, in our opinion, in the pilot line stage. The first example is our work on integrated comp sources, which is obviously very important for people who are looking into dense wavelength multiplexing. Here you see some very nice measurement results where you see that we get 15 usable comp lines out of an integrated comp source, which has an acceptable temperature dependence. We also get nice eye diagrams, bit error rates less than 10 to the minus 12 as we want. So that's a project where we're heavily working with pilot lines to make that more mature. Another project that we're looking into is silicon germanium avalanche photodiodes, where you see some recent results. More details can be found in the Optica papers or the conference papers listed at the bottom of the slides. But basically, by changing the geometry in very clever ways, we're able to reduce the breakdown voltage. We're able to get gain bandwidth products of, say, 300 gigahertz, very good sensitivities. So there's a lot of developments that we've recently done in the last couple of years that actually only was possible by our access to some very reliable pilot line foundries. In this case, this is done through collaboration with Leti, for instance. And then a final project that I want to talk about is our work on quantum dot photodetectors, where we were looking into, can we use the same epitaxial structure that we use for our lasers, but instead of developing lasers, can we use it for photodiodes? And the answer is yes, we can do this. And surprisingly, we even found a signature of avalanche effects there. So we got gain at room temperature of around 45. And so this is also a more recent project where we are working more and more with pilot line foundries to make this more mature. Okay, so those are the examples. Then seeing ourselves as a user of pilot lines, what are the metrics that we keep in mind when we make our decision on which foundry we want to use? There are some things listed on this slide. I don't think there are very big surprises there. There's obviously the cost, the technological capabilities, the flexibility that we have in the design tools, the turnaround time. But I need to emphasize here that from our perspective, IP policy is really key. So if you're a very good pilot line foundry, and even if you have the best technological capabilities out there, but your IP policy is not really in line with our commercialization strategy, then we probably will not work with you. Another thing that is getting more and more important for us is that if a pilot foundry already has a partnership with a volume foundry, that gives us outlook on an easier transfer of our research in the pilot line foundry to what we can do in a volume foundry. And obviously that reduction in time to be able to do that transfer is a lot of money, it's worth a lot of money for us. So that's also something that will help us making decisions if that's there. So in conclusion, what did I talk about? I talked about how HPE is currently looking into silicon photonics for the applications that are of relevance for HPE. Key there is our access to pilot lines. Without pilot line foundries, we would not be able to do the work that we have to do. And in addition to the requirements that we have for pilot line foundries, I also briefly talked about measurement automation that we need, and also design automation that we need to make our jobs as engineers more efficient in developing this PDK. And with that, I want to conclude my presentation. And I think now it's time for questions. Thank you.
Thank you very much, Thomas, for your contribution. This was the recording, but there you are. You are also here, live in the chat. So thanks a lot for your talk, because it's actually what the dream. If we were now in an epic meeting, we would say, the end users, and the end users already said the points that are good or bad for the pilot line. So thank you very much for this, especially this on the IP regulations was a thing that we heard at the beginning already from Robert, but is very important. So basically, your approach is really like either it's a good one or you are out, right?
Fair enough, yeah. Because we need to engage normally for multiple runs with a foundry partner. So at first we decide whether we want to go with them, and after that you already build a technological relationship with a partner, and it doesn't really makes too much sense to keep on switching after that. So that's why it's a part of the decision-making process very early on.
Yeah, and it's good that you presented already when you say, look, we would really like to work for you, but there are these points to be respected, and that's the perfect way to get the collaboration working and running. So we have some question now from the audience. So a bit more on the technical side, so also to know what you are doing. So there is this one, I guess, is referred to one of your examples. So for the circuits with the hundreds of rings, do you use some kind of DST to reduce the testing time, or you have other strategies?
This is something that we're currently still working on. And to be honest, in the labs team, in the photonics team, you have some people who are more working on further out there research. I think I can consider myself to be part of that part of the team, whereas some other people are working more on the, towards development of the technology, towards volume fabrication. So those folks are working on this. What I see happening there is that actually in this message that I gave about we see an ecosystem, we don't want to do everything just by ourselves. We try to engage with other partners that are out there that actually help us enable coming up with testing solutions. So we give our own input of our experience of how do we need to do automation of the silicon photonics measurements, but then we also try to leverage what developments they already have done for other partners, so that we don't have to reinvent the hot water or something. So I can't give a very specific answer to that because it's still something that we're working on, but yeah, it's something that we keep in mind.
Yeah, maybe the question owner wants to help, who knows? Maybe you can connect offline and discuss further this, why not? And also, the question was also from the same person about the volume. So how much are you talking about from the fabs that you receive?
Yeah, I think for that, for instance, we are now working on this program called PAD4. It's almost finished, and that was to make an exascale computing system. We were counting on having 500,000 optical interconnects in there based on silicon photonics. So you can kind of do the math based on how large a chip is, which is kind of the size of your thumbnail, I guess. And then you end up with having a couple of thousands of wafers for just that one single system. So obviously we would also like to not just one single system, we would like to branch out and eventually sell that technology also to other customers. So that gives you an order of magnitude of what we're dealing with, and that's what, when we talk about volume foundries, we're specifically talking about foundries that can actually offer that type of potential. But at the same time, we also, again, in this mission of working in an ecosystem and not trying to do everything vertical, we also hope to enable other customers of that same foundry to use our technology. And that's one of the reasons why we're thinking on commercializing our open PDK through some kind of a licensing scheme so that other people can use it, and so that if it's not only our demand that would be the volumes that would drive that foundry, but also other customers could come in with their use case, and by doing that also drive up the volume in that way. I hope that kind of answers that question.
I guess it was kind of precise. So thanks a lot for your contribution. So and in general, thank you very much for really your detailed description. As I said, we look forward to have you maybe also on some epic events where you can really say, we want this and it has to be like that, otherwise you're out. So this is a clear statement that are really useful for collaboration. So thanks a lot, Thomas, again. And then we go forward to the next speaker. So from PIC Advanced, we have the contribution from the CEO, that I see also is there, but we have also the recording. So just now to introduce a bit the talk. So next generation passive optical networks 2 is a great challenge and a great opportunity for telecommunication operators to cope with the bandwidth demand. Introduces a whole set of new possibilities in the network through the tunability of the ONUs, and bringing new physical layer capabilities will establish a whole new world of flexibility. PIC Advanced is already available a commercial solution for NGP-ON2, ONU, and transceivers, and running at a fast pace to have the optical integration as its engine. The solution enhances not only the tunability, but also the performance, size, and power consumption. And PIC Advanced is going to present the current developments in the topic and show the current path from the proof of concept to solution. So thank you very much for being here, Francisco.
Thank you very much for the invitation.
Now, the floor is for the recorded Francisco.
Hello, my name is Francisco Rodrigues and I'm here to present to you PIC Advanced and Picturizing Transceivers. The presentation will have three main moments: a company presentation so that the ones who are not acquainted with PIC Advanced start to get to know it. And then I will move to NGPON2 solutions, the ones that we have been developing over time. And I will finalize with Picturizing Transceivers to present the platform that we are developing for optoelectronic transceivers based on photonic integrated circuits. PIC Advanced was founded in 2014, and today, in 2020, we are a team of 20 people that have strong knowledge on photonic integration. The company was founded by António Teixeira, who is a full professor at the University of Aveiro, and he is a researcher with a strong background on access networks and photonic integration. The other person that was a co-founder is Ana Tavares, who was working with António in 2014, doing research on photonic integration for NGPON2, making this the right team to start PIC Advanced. We are located in Portugal, in the north, in Aveiro, and very close to our headquarters, we have the University of Aveiro campus, where state-of-the-art research is done on materials, physics, electronics. And the campus also comprises the national headquarters of Telecommunication Institute of Portugal, where also very good research, state-of-the-art, is done on photonic integration and different types of networks. The company PIC Advanced offers a wide variety of services that can be divided in three main platforms. The first one is the electronics, where we can develop PCBs and electronic systems and components with high level of integration based on FPGAs, processors, and also focused on RF performance, where we have already developed PCBs with multiple lanes that can go up to 40 gigahertz. We can also do assembly and testing of the boards so that we can offer turnkey solutions to our customers. On the PIC side, we can offer services on the simulation and design of photonic building blocks and also on architectures for photonic integrated circuits based on a target performance. We also offer services of packaging through our proprietary platform that we have been developing throughout the years and that I will address later on the presentation. We also can do services on testing and characterization, not only on the component level, but also on the packaged module level based on photonic integrated circuits. The last pillar is the firmware and DSP, where we focus on embedded systems targeting optoelectronic transceivers and the control of the photonic components, and DSP, where we are focused now on forward error correction algorithms of 400G and 800G networks. We also have a strong know-how on fiber impairment compensations. The PON market is the market that PIC Advanced has been mainly addressing since the beginning. It started with the GPON, which is a time division multiplexing that has a point-to-multipoint connection, and evolved to NG-PON2 that can offer at least 4 times the bandwidth that GPON offers, and is the only standard that can comprise multiple wavelengths, offering time and wavelength division multiplexing. This means that at the ONU side, the client side, the optics that are deployed need to be tunable. This tunability is a challenge that associated with the challenges of the PON that are high power budget, meaning high power transmitters and high sensitivity receivers, low power consumption and low cost, create all the challenges that we needed to address to develop NG-PON2 transceivers. And we have achieved it. We have launched ONU that is NG-PON2 fully compliant, where the laser is a DML that can reach 10 gigabits per second, 20 kilometers, meaning that we had the strong modeling in firmware for our lasers. The receiver is high sensitivity APD, where the receiver is also thermally tuned. And talking about tunability, the class 2 and 3 that we address in the slides means all the tuning time between any combination of channels, minimum required number of channels on NG-PON2 is 4, to be less than 25 milliseconds. And we also achieved it. In terms of temperature of operation, iTemp, which is the more broad, needs to operate from -40 to +85 degrees C, and all the remaining characteristics of the transceiver needs to maintain, meaning that we have developed models and algorithms that allow our photonic components to withstand such a wide variation of temperature and maintain its tunability requirements. These are products that are in production. We have developed a production line that is fully automated and that where we do all the testing that is required for all the NG-PON2 parameters, offering high quality NG-PON2 products to the market. In this road to TWDM, we are developing more products. One that we like to feature is the NG-PON2 stick. Also, we are developing NG-PON2 OLT that is based on DML with the lessons learned from the ONU developments, and of course our PIC-based transceiver platform for NG-PON2. On the stick that I have addressed in the first bullet point is the summation of what is an optical network terminal, an ONT, a box like this that has a processor with the routing and layer 2 functionalities of the NG-PON2, with the transceiver that has the physical requirements that I also addressed, all together in a small form factor like SFP+, enabling the NG-PON2 stick. This is a product we are developing and we are going to launch this year that is NG-PON2 compliant and comprises layer 2 functionalities. Of course, that this presentation is all about photonic integration, and this panel is about photonic integration. And it is the work that we also have been addressing since the beginning of PIC Advanced. We want to replace the current poses that we have on our products with PICs. So all the functions in a single chip, as we are targeting monolithic integration, that will be 100 times less volumetric. This integrated solution will also comprise half of the electrical assembly steps and 5 times less the optical alignment processes, as everything is integrated. And this is the platform that we are developing. We can do layout and simulation, packaging, test and characterization. We don't do fabrication as we are fabless. The platform that we are developing already comprises proprietary building blocks that were simulated and were designed to meet the required reduced floor space, meaning that for example, for NG-PON2 ONU, we reached indium phosphide monolithic integration with sub 8 square millimeters per chip. The high sensitivity that is required for the access networks was achieved through architecture developed by us that implement quasi-coherent receiver. In terms of the packaging platform that I have addressed before, it is based on a holder that you can see here in almost in the point of our fingers, and this packaging platform allows one to place the PIC, align the fiber, and also have electrical connections and thermal management of the whole system, as we can do efficient thermal management with embedded as planar linear sensors deposited in the holder. With the development of this older platform, we have also developed RF performance optimized. Here in the pictures, you can see already some transceivers with the PICs packaged in our older platform, already with some RF interposers for our first demonstrations. Platform that we have developed and tested so far shown a transmitter 3 dB bandwidth of 25 GHz, which is in excess of the 10 gigabits per second that we need for now. In the receiver side, up to 40 GHz. We achieved the coherent detection through photonic integration, and in the building blocks that we have developed proprietary polarization and band splitting components. This was tested and characterized already in our labs, and you can already see here an XFP with a PIC package in our holder platform. This was our first prototype that we developed here in PIC Advanced. I will invite you, everybody, to visit our store so you can see the different transceivers that we have for sale, and also the services that I have been talking about and I talked before are also available per inquiry in our website and online store. Thank you for your time, and I'm open for any questions that may arise.
Thank you very much, Francisco, for your contribution. So now we are back here in the room. There you are. So it was a really interesting contribution also because compared to what we were saying so far, there was, let's say, the open questions, let's say the open discussion between horizontal and vertical integration. So those who go like the pilot lines, of course, horizontally, so with a lot of partners and try to get a foundry or at least a service for external partners and customers. And also those who go more on a solo activity. And from what I understand, you are kind of really well organized on your own, but still you are fabless. So it would be nice to hear from you what is your experiences in collaboration with the fabrication supporters and how you deal with it in view of what other pilot lines can learn from you.
Yes, first of all, thank you very much for the invitation. Concerning your question, I would say that we are an hybrid. We like to develop know-how on the diverse areas that we stated before, the electronics, the packaging, and also on the PIC design, as we need to customize the solutions for an addressable market that in this presentation we presented as NG.2, but more on the network space. Of course, that as a company, we can never live alone. You cannot survive on your own island. So we do have partnerships, first with the foundries, where we do the fabrication of the indium phosphide chips. And also for the packaging platform, we also established some partnerships. And we try to take advantage of the different projects that are undergoing. We have early users of JPICs as a company, through MPW experiments to start to develop our platform. Also, we currently have a PICSAP project undergoing to extend the capabilities of the designs that we have, and also extend what we can learn from other partners and what we can do in-house. So we try an hybrid approach where most of the know-how is also built in to customize for the applications that we need.
Very good, because this is exactly also one of our aim, why we're sitting here. So you mentioned already you're collaborating, and you're also is a learning point from other pilot lines. So that's very good that you are well connected also in this network, and that you hopefully also in the future can work on also when these pilot lines are over and they are in their development phase, and you can still cooperate. Then we have also a question from one of the attendees, and they are asking, why are you targeting monolithic integration?
It's a very good question. It's not easy to answer, but for our specific market, we know that has the right target price, and we observed through the different architectures that we could exploit, that having the trade-offs, all the trade-offs in indium phosphide would be the best way to reach that. We need definitely in the telco application, we need the amplification and the lasers. So we would need to have again a medium in our solution, and then on the passive side, we need to overcome some of the losses and how to deal with the polarization and reduced footprint. And that's the challenge that we addressed and overcome and are overcoming. On the packaging side, it gets easier if you meet the prior that I've stated before, because you would package only one chip instead of trying to package two in a 2D or 3D integration manner.
Okay, thank you very much. I guess that was explanatory enough. So I guess now we have arrived at the end of this path that we have today for us in the afternoon in Europe and for maybe US in the morning or late morning. So it was really a pleasure for me to be here to moderate these discussions. And I really thank you, the AngelTech organizer, for letting me do this and for organizing such a session. Also, strictly talking about this session where really pilot lines and also other experiences can confront with each other, and also strengthen, let's say, collaboration that were already there, but also promote new collaborations. So we had a really a nice overview of new pilot lines, old ones, let's say more experienced ones, those who are still on the way, and also from external experiences out of European funded initiatives. So I would say I would like to thank you all, also the speakers that were here for all this time, and also for nice exchange with each other, and also the attendees that offline could also reach out, fortunately, with some questions. So it was really nice to be here as a chair. So I thank you also to the European Commission and for the financing of these fantastic pilot lines that we had, but also that it's nice to see that also initiatives own initiatives are also running. So thank you very much, and see you next time, hopefully in person, hopefully. Bye-bye.
Thank you. Bye, Francesca.
Thank you. Bye-bye.